Imagine staring up at a sky filled not just with stars, but with something deeper, an ancient, silent echo that has been traveling across space for nearly 14 billion years. What if I told you that the universe has its own baby picture, and it's not just a faded memory, it's a living, breathing snapshot of the cosmos in its infancy, and it may hold secrets that challenge everything we think we know about reality, time, and our place in the grand scheme of things. This isn't science fiction. It's written in the oldest light there is, the cosmic microwave background, or CMB for short. This ethereal afterglow of the Big Bang blankets the entire universe, a whisper from the very moment everything began. It's the oldest thing we can observe, and yet it's anything but simple. Scientists first detected it by accident in the 1960s, and since then it has reshaped our understanding of the cosmos. But here's what's truly astonishing. The more we learn, the more we realize how much we still don't understand. Hidden within that faint microwave static are not just answers, but profound mysteries, 30 of them in fact, that continue to baffle the brightest minds on Earth. From unexplained cold spots to strange alignments that defy the laws of physics, these aren't just academic curiosities. They're clues pointing toward something bigger, something beyond our current grasp. This video is your invitation to join a journey into the unknown, to explore these enigmas one by one and witness how they're reshaping our story of the universe. You're about to step into a world where the rules we take for granted might not apply, and where each discovery brings us closer to truths that could redefine reality itself. So settle in, open your mind, and let's uncover the secrets written in the oldest light there is. Our journey into the cosmos's deepest secrets begins with perhaps the most fundamental puzzle of all, one so profound it forced scientists to rewrite the very first chapter of our universe's story. This is the horizon problem, and it asks a deceptively simple question. How did the entire universe decide on the same dress code? When we look out at the cosmic microwave background, we see something that, at first glance, seems wonderfully peaceful. The temperature is almost perfectly uniform, varying by less than 1 part in 100,000. To put that incredible level of sameness into perspective, it would be like smoothing out the entire surface of the Earth until the highest mountain and the deepest ocean trench were less than 100 meters apart. This is a universe that appears to have been mixed into a perfectly consistent batter. But this serenity is actually a colossal problem for the classic Big Bang model. Here's why. The universe has a speed limit, the speed of light. Nothing, not even information about temperature, can travel faster. Now, think about two opposite sides of the observable universe. The light from the CMB has been traveling for nearly 14 billion years to reach us. That means we are seeing those distant regions as they were in their infancy, just 380,000 years after the Big Bang. And here's the catch: in all that time since the beginning, light simply has not had enough time to travel from one of those distant points to the other. They are, and always have been, completely cut off from each other, beyond each other's cosmic horizon. They are like two strangers stranded on islands in a vast, expanding ocean, too far apart to have ever shouted to one another. So how did these isolated regions, these cosmic strangers who have never exchanged a single photon, somehow agree to have almost exactly the same temperature? It would be like walking into a vast, crowded party where every single person, without having ever spoken, is wearing the exact same shade of blue shirt and khaki pants. Under the standard rules of physics, this shouldn't be possible. There was no mechanism for them to reach this thermal equilibrium. This wasn't just a minor inconsistency, it was a glaring flaw at the very heart of our understanding, suggesting we were missing a monumental piece of the cosmological puzzle. The solution that emerged, known as cosmic inflation, is as elegant as it is mind-bending. It proposes that in the first fleeting fraction of a second after the Big Bang, the universe underwent a period of exponential, faster-than-light expansion. Think of it like this. Picture a tiny, subatomic-sized speck of space. This speck is so incredibly small that every part of it is in intimate contact, allowing it to easily settle into a uniform, cozy temperature. Then, in an instant smaller than a trillionth of a second, this speck is stretched to a size larger than our entire observable universe today. This rapid inflation took that initial, small, uniform region and blew it up to become everything we can see. The distant points that now seem forever isolated were once right next to each other, able to chat and coordinate before being dramatically pulled apart. Inflation solves the horizon problem by giving the entire observable universe a common, connected origin story. Yet, while inflation is our leading theory, it remains just that, a theory. We have compelling mathematical models, but the search for direct, observational proof of inflation itself is one of the great ongoing quests in modern cosmology. But if the horizon problem made us question the universe's need for a connected past, the next mystery challenges something even more foundational, the very shape of reality itself. This is the flatness problem, and it asks why the fabric of the cosmos isn't curved, warped, or crumpled, but instead appears to be almost perfectly, impossibly flat. When we talk about the universe being flat, we're not referring to its physical shape like a sheet of paper. Instead, we're talking about its geometry, the rules that dictate how parallel lines behave and the angles inside a triangle. In a universe with positive curvature, like the surface of a sphere, parallel lines eventually meet and the angles of a triangle add up to more than 180 degrees. In a universe with negative curvature, like a saddle, parallel lines diverge and triangle angles sum to less than 180 degrees. But in a flat universe, the rules are the simple Euclidean geometry we learned in school. Parallel lines never meet, and a triangle's angles always add up to exactly 180 degrees. The cosmic microwave background is our most powerful tool for measuring this cosmic geometry. The patterns of hot and cold spots in the ancient light act like a giant ruler. The apparent size of these fluctuations tells us whether the light rays that created them have been traveling in straight lines or if they've been bent by the curvature of space itself. And the measurements from satellites like Planck are astonishingly precise. They tell us that the universe is flat too, within a margin of error of just 0.2%. The density parameter, represented by the Greek letter omega, is incredibly finely tuned to exactly 1. A value greater than 1 would mean a positively curved, closed universe that would eventually collapse in a big crunch. A value less than 1 would indicate an open, negatively curved universe that would expand forever into a cold, empty void. Our universe at exactly 1 is perfectly balanced on this knife edge, destined to expand forever but at a rate that slows infinitely towards 0. This is where the problem lies. This perfect balance is incredibly unstable. Think of trying to balance a pencil perfectly on its point. The slightest breath of air, the tiniest vibration, would knock it over. Now imagine that pencil has been standing on its point for nearly 14 billion years. That's the level of fine-tuning we're talking about. For the universe to be this flat today, in the first second after the Big Bang, the value of omega must have been tuned to 1 with mind-numbing precision, to within 1 part in 10 to the power of 60. That's a 1 followed by 60 zeros. To say this is unlikely is a cosmic understatement. It seems virtually impossible by random chance. This incredible fine-tuning demands an explanation. How did the universe get this perfect balance between its expansion energy and the gravitational pull of all its matter and energy right from the very start? Once again, the theory of cosmic inflation provides a powerful answer. That same period of hyper-fast expansion would have acted like a giant cosmic iron, stretching the fabric of spacetime so dramatically that it would smooth out any primordial curvature, inevitably driving the universe toward the flat geometry we observe today. It doesn't require an inexplicably perfect starting condition. It takes a wide range of initial shapes and flattens them all out. Inflation doesn't just solve the flatness problem. It predicts the flat universe that we later went out and discovered. This beautiful convergence between a theoretical prediction and an observational reality is what makes science so powerful, yet it also leaves us with a humbling thought. The very geometry of our reality, something that feels so fundamental and fixed, might simply be a local artifact, a consequence of a violent inflationary event in our pocket of a much larger and possibly very different multiverse. Yet if the horizon and flatness problems revealed a universe that needed a cosmic reset to explain its current state, the next mystery points to something that should be here but is conspicuously absent. It's the case of the missing monopoles, and it involves a hypothetical particle so fundamental that its absence threatens to unravel our entire understanding of the forces that govern reality. To understand why this missing particle is such a big deal, we need to rewind the cosmic clock back even further than the moment captured by the CMB. We go back to the first fractions of a second after the Big Bang, to a time of almost unimaginable energy and temperature. In this primordial furnace, the four fundamental forces we know today, gravity, electromagnetism, and the strong and weak nuclear forces, were not separate. Physics tells us they were unified into a single, supreme force. Theories that describe this era are called Grand Unified Theories, or GUTs for short, and they make a stunning prediction. As the universe expanded and cooled, it underwent a series of dramatic phase transitions, much like steam condensing into water or water freezing into ice. And just as freezing water can create cracks and fissures in ice, these cosmic phase transitions should have created topological defects in the fabric of spacetime itself. One of the most fascinating of these predicted defects is the magnetic monopole. Think about every magnet you've ever encountered, from a simple fridge magnet to the Earth itself. They always have two poles, a north and a south. You can break a bar magnet in half, but you won't get an isolated north and an isolated south. You'll just get two smaller magnets, each with its own north and south pole. A magnetic monopole would break this rule entirely. It would be a particle that is just a pure north magnetic pole, or just a pure south with no opposite. It would be a fundamental, isolated magnetic charge. According to grand unified theories, these monopoles wouldn't be rare curiosities. They should have been produced in staggering abundance during the universe's early moments, a byproduct of the forces splitting apart. They would be incredibly massive, stable, and persistent. They wouldn't decay over time. In fact, the calculations suggest that monopoles should be so numerous that they would outweigh all other matter in the universe. They would dominate the cosmic energy budget, making the universe incredibly dense and causing it to recollapse long before stars, planets, or life could ever form. We should be swimming in a sea of monopoles, and yet, despite decades of searching with incredibly sensitive detectors, not a single, definitive magnetic monopole has ever been observed. It's as if we've predicted an entire ocean exists, but we can't find a single drop of water. This glaring contradiction between a beautiful theory and a complete lack of evidence presented a major crisis for cosmology. If our theories about the universe's grand unification were correct, then monopoles must exist, but they clearly don't. So, was the entire idea of grand unification wrong? Once again, the theory of cosmic inflation provides an elegant and powerful solution. Remember that period of exponential, faster-than-light expansion. It wouldn't just smooth out the temperature and flatten the geometry. It would also act as the ultimate cosmic vacuum cleaner. That hyper-fast stretching of spacetime would have diluted the density of any primordial monopoles to virtually zero. It would have spread them so thin across the vastness of the cosmos that finding one in our observable universe becomes statistically improbable to the point of being nearly impossible. In this way, the profound absence of evidence becomes some of the strongest evidence we have. The fact that we do not see monopoles is a powerful clue that an event like inflation must have occurred, sweeping the cosmic slate clean and leaving behind the universe we see today. It's a brilliant resolution, turning a theoretical failure into a triumphant prediction. But this solution, while elegant, opens the door to an even deeper and more unsettling possibility. If inflation can erase something as fundamental as magnetic monopoles, what other relics from the true beginning of everything might it have washed away, leaving us with a universe that only tells part of its own story? Yet, just as we find comfort in the elegant solutions of cosmic inflation, a discovery from the early 2000s sends a chilling ripple through the world of cosmology, one that seems to pull the entire universe back toward us in a deeply unsettling way. This is the mystery known as the axis of evil, a name that perfectly captures the profound threat it poses to a fundamental principle of modern science, the Copernican principle. This principle, which has been a cornerstone of cosmology for centuries, states that we do not occupy a special or privileged place in the universe. The Earth is not the center of the solar system, the Sun is not the center of the galaxy, and our galaxy is not in some unique central location. The universe on the largest scales should be isotropic and homogeneous. It should look the same in every direction, with no preferred axis or central point. The cosmic microwave background has long been hailed as the ultimate proof of this idea. Its stunning uniformity shows us a cosmos that is broadly the same everywhere, a smooth, featureless sea of ancient light. Or so we thought, when scientists from the Wilkinson Microwave Anisotropy Probe, or WMAP, began analyzing their incredibly detailed map of the CMB. They expected to see randomness. The tiny fluctuations in temperature, those seeds for future galaxies, should be scattered across the sky like a random spray of paint with no discernible pattern or alignment. But that's not what they found. To their astonishment, they discovered that some of the largest scale fluctuations, the biggest hot and cold spots in the universe, were not randomly oriented at all. Instead, they appeared to be aligned with what we call the ecliptic plane, the plane of Earth's orbit around the Sun. It was as if the universe's largest structures were somehow aware of our tiny, insignificant solar system. The implications of this are nothing short of horrifying for a cosmologist. It suggests a correlation between the entire observable universe and our local cosmic backyard. This is not just a minor statistical fluke. It's like discovering that the foundation of a skyscraper is perfectly aligned with a single specific window in your apartment. The scale is all wrong. The cosmic microwave background is the most distant thing we can see, a signal from the edge of space and time. Our solar system is an infinitesimal speck by comparison. For there to be any connection between the two violates our deepest understanding of cause and effect and scale. It hints that we might be seeing some kind of contaminant, a shadow of our own solar system imprinted on the most ancient light, or worse, that the universe itself has a preferred direction that just happens to line up with us. The scientific community has grappled with this anomaly for years. The leading and most hoped-for explanation is that it's a systematic error, a flaw in our measurement or analysis that we haven't yet identified and corrected for. Perhaps the way our satellites scan the sky, or the way we subtract the foreground glow of our own galaxy, is inadvertently creating this bizarre pattern. But despite rigorous checking and reanalysis of data from later missions like Planck, the strange alignment stubbornly persists. It refuses to go away. If it is real, the consequences are staggering. It could mean that the Copernican principle is wrong, and that we do, in fact, live in a special place in the cosmos, a thought that modern science has utterly rejected. It could indicate that our universe is not isotropic, but has a large-scale structure or flow that we are only just glimpsing. Some have even proposed more radical ideas, like that our universe collided with another universe in the multiverse, imprinting a direction onto the fabric of reality itself. The axis of evil remains an open wound in cosmology, a persistent warning that our map of the universe may still have a "you are here" arrow pointing directly at us, and that the cosmos might not be as impersonal and random as we have always believed. And just when we think we've mapped the major anomalies, the cosmic microwave background reveals a feature so bizarre and vast that it seems to defy explanation altogether. This is the mystery of the cold spot, a colossal region of space that isn't just a little bit cooler, but profoundly and unnervingly cold on a scale that is difficult to even comprehend. Nestled in the constellation Eridanus, this area isn't a tiny blip on the map. It spans a staggering 1.8 billion light-years across. To put that impossible scale into perspective, if our entire Milky Way galaxy were the size of a dime, the cold spot would be larger than the entire Earth. It is a cosmic supervoid of truly epic proportions, a vast and seemingly empty desert in the fabric of the universe where the temperature of the ancient light is markedly lower than the average. This isn't a statistical fluctuation that can be easily dismissed. Its size and its coldness are so extreme that, according to our standard models of cosmology, the odds of such a feature forming by random chance are less than 1 in 200. It is an outlier that screams for our attention. So, what could possibly create such an immense and frigid anomaly? Scientists have proposed several theories, each more incredible than the last. The first and most straightforward explanation is that we are literally looking at a nothingness so profound it bends the laws of physics. This is the supervoid hypothesis. The idea is that this region of space contains far fewer galaxies and clusters than it should, a vast underdensity of matter. Now, according to Einstein's general relativity, photons of light lose energy as they climb out of a gravitational well. But what happens when a photon travels through a void, an area with significantly less gravity? It should actually gain a tiny amount of energy, making it slightly hotter, not colder. This is known as the integrated Sachs-Wolf effect. The cold spot presents the exact opposite problem. To make it so cold, a supervoid would have to somehow make photons lose energy, which goes against our current understanding. It's as if a ball rolling down a hill suddenly slowed down instead of speeding up. This has led many cosmologists to question if a simple lack of matter is enough to explain this profound cold. Perhaps the void is even larger and emptier than we can currently measure, or maybe our understanding of how light and gravity interact on the largest scales is incomplete. When a conventional explanation falls short, we must turn to more exotic possibilities. One of the most fascinating is the concept of a cosmic texture. In the ultra-high energy physics of the early universe, as the fundamental forces were breaking apart, they may not have done so perfectly smoothly everywhere. Think of it like water freezing on a pond. Most of the surface forms a smooth sheet of ice, but occasionally the molecules don't align perfectly, creating a tiny defect or a crack. A cosmic texture would be a similar kind of defect, but in the very fabric of space-time itself. A knot of concentrated energy left over from the primordial phase transitions. If such a texture existed and we were to pass through it, it would have a dramatic effect on the light from the CMB, creating exactly the kind of intense cold spot we observe. It would be a direct frozen relic from the first moments of time, a cosmic fossil imprinted on the sky. The thrilling part of this theory is that it is potentially testable. If the cold spot was caused by texture, it should have a very specific signature in the polarization of the light around it. Future, more sensitive telescopes could go looking for this fingerprint. But the most radical and mind-expanding theory is that the cold spot is not a feature of our universe at all, but evidence of a collision with another universe. This idea comes directly from the theory of the multiverse, which is itself a prediction of eternal inflation. The theory suggests that our universe is just one bubble in a vast, frothing cosmic foam of universes, each with its own distinct physical laws. In this incredible scenario, our expanding universe bubble might have collided with a neighboring bubble in the multiverse while both were still inflating. The energy released at the boundary of that collision would have been immense, and it would have left a permanent bruise on our cosmos, a circular imprint of altered temperature that we now observe as the cold spot. This wouldn't just be a mystery solved, it would be the first empirical evidence that our universe is not alone, that there is a greater meta-reality beyond our own cosmological horizon. It would be a crack in the sky, offering a fleeting glimpse into the infinite beyond. The cold spot remains one of the most tantalizing and persistent enigmas in all of cosmology. It is a celestial Rorschach test where scientists see the evidence for their most profound theories. From cosmic defects to other universes, its very existence challenges the limits of our models and dares us to think bigger, to consider that the ancient light we see may hold clues not just to our own origin, but to realities we are only beginning to dream of. Yet, even as we grapple with the large-scale shock of the axis of evil and the immense void of the cold spot, the cosmic microwave background reveals that its anomalies are not confined to the grand and the gigantic. Some of the most perplexing clues are written in the very lowest notes of the universe's first chord, in the largest and most fundamental patterns imprinted on the sky. This brings us to the subtle but deeply troubling mystery of the quadrupole and octupole anomalies. To understand what these are, we need to think about how scientists decipher the CMB. They don't just look at a picture, they listen to its music. The patterns of hot and cold spots can be broken down into a cosmic symphony of different frequencies. Much like a complex musical chord can be separated into its individual notes, the deep bass, the mid-range tones, and the high treble. In cosmology, these notes are called multipoles. The lowest notes, the largest scale patterns, are the quadrupole, which is like the second note, and the octupole, the third note. These represent the most fundamental, sprawling temperature variations across the entire sky, the biggest waves in the ancient sea of light. In a universe that is truly random and isotropic, the same in all directions, these largest patterns should be just that, random. The hot and cold spots of the quadrupole and octupole should be oriented arbitrarily, with no correlation to each other and certainly no special alignment with any local structure. They are a message from the farthest edge of the observable universe and should be completely disconnected from our tiny neighborhood. But when scientists from the WMAP and later the Planck mission analyzed these low-order multipoles, they found something that sent a shiver through the community. The quadrupole and octupole moments are not random. Their axes are oddly aligned with each other, and even more bizarrely, they show a strange preference for a single plane across the sky. A plane that intriguingly and disturbingly seems to correlate with the ecliptic, the plane of our own solar system. Let's be clear about why this is so problematic. Imagine you are listening to a symphony performed by an orchestra on a stage a mile away from you. The deepest, most resonant notes from the tubas and timpani are the quadrupole and octupole. Now, imagine you discover that the rhythm and pitch of those deep notes are somehow synchronized with the gentle hum of your own refrigerator. The scales are so vastly different that any connection is absurd. That is the essence of this anomaly. The largest possible structures in the entire cosmos appear to be whispering a secret that involves the infinitesimally small arena of our solar system. It's a violation of scale that threatens the cosmological principle, the foundational idea that the universe has no center and no special direction. The immediate and most hoped-for explanation is that this is a systematic error. Perhaps the way we process the data, the way we subtract the foreground glow of our own galaxy, or even the residual heat from dust within our solar system, is inadvertently imprinting this local signature onto the most ancient of maps. Scientists have gone to extraordinary lengths to root out such contamination, meticulously cleaning the data of any known local interference, but the alignment persists. It stubbornly refuses to be washed away, suggesting that if it is an error, it's an incredibly subtle and clever one that has so far evaded our best efforts to find it. If it is not an error, the implications are profound. It could suggest that our universe is not isotropic on its very largest scales. Perhaps it has a preferred direction or a subtle curvature we haven't yet accounted for, a fundamental lopsidedness to reality itself. Some theorists have proposed even more exotic ideas, such as that the universe might be finite and have a non-trivial topology, meaning it could be shaped like a torus, a donut, or another complex form. And these low multipoles are giving us a hint of its overall shape, a shape that would force correlations across the sky. Others have wondered if it could be a sign of pre-Big Bang physics, a relic of whatever process spawned our universe, forever frozen into its first light. The quadrupole and octupole anomalies are a quieter mystery than the colossal cold spot, but in many ways they are more insidious. They are not a single dramatic flaw in the cosmic canvas, but a slight warping of its very frame, a suggestion that the foundation upon which we've built our entire model of the cosmos might be ever so slightly crooked. They serve as a persistent, low-frequency hum in the background of cosmology, a constant reminder that our understanding of the universe's infancy is still incomplete, and that its first whispers may still be telling us a story we have not yet fully learned how to hear. But if the largest scale patterns of the quadrupole and octupole gave us a subtle hint that the cosmos might be lopsided, the next mystery removes all doubt with a shocking and blatant violation of cosmic etiquette. This is the hemispherical asymmetry, a finding so straightforward in its imbalance that it directly and brazenly challenges the foundational rule that the universe must look the same in every direction. The cosmological principle isn't just a nice idea, it's the bedrock upon which almost all of modern cosmology is built. It states that on the largest scales, the universe is homogeneous and isotropic. Whether you're in a galaxy far, far away or right here in the Milky Way, the overall view of the cosmos should be essentially the same, a vast, uniform expanse with matter and energy evenly distributed. This principle allows us to extrapolate from what we see in our observable bubble to make assumptions about the entire universe. It's what makes cosmology a science rather than pure guesswork. The cosmic microwave background has long been the ultimate evidence for this principle, its near-perfect uniformity a testament to a well-mixed and balanced cosmos. But that pristine image is now cracking. When scientists from the WMAP and later the Planck mission created their exquisite maps of the CMB's subtle temperature variations, they decided to run a specific test. They divided the sky into two hemispheres and calculated the average power or the strength of those temperature fluctuations in each half. In a perfectly isotropic universe, the statistics should be identical. The results, however, were anything but. They revealed a startling and consistent asymmetry. One half of the sky, roughly in the southern hemisphere, shows significantly stronger temperature variations than the northern half. It's not a tiny, marginal effect. The difference in power is on the order of 10%. To put it in simpler terms, imagine the universe's baby picture has one half that is noticeably grainier, more textured, and more dramatic than the other, which appears comparatively smoother and more placid. This is not a subtle statistical quirk, it's a glaringly obvious feature. It's as if you painted a room with two identical cans of paint, using the same roller technique, but one wall dried with a much more pronounced and rougher texture than the other. The very presence of this asymmetry forces us to ask an uncomfortable question. Is there a preferred direction to the universe? Does the cosmos have a more active and a more quiet side? And if so, what could possibly cause such a fundamental imbalance on the grandest of scales? The most conservative explanation is once again that we are being fooled by foreground contamination. Perhaps the way we are removing the light from our own galaxy is imperfect, leaving behind a residual signal that makes one half of the CMB map appear more powerful than the other. Or maybe there is an unknown cloud of dust or gas within our own solar system that we haven't fully accounted for, casting a shadow that creates this illusory effect. Scientists have chased this possibility relentlessly, but the asymmetry persists even after the most aggressive and thorough data cleaning. It seems to be a genuine feature of the primordial light itself. If it is real, the implications are profound. It suggests that the conditions in the very early universe were not perfectly uniform. The seeds for all future structure, the galaxies and clusters we see today, may have been sown more densely in one part of the primordial soup than another. This could mean that the process of inflation, the theorized period of hyper-expansion that smoothed the universe, did not finish its job completely. Perhaps it didn't run for long enough in all directions, or maybe the field that drove inflation had a slight gradient, a tilt, that created a directional dependency in the energy it imparted. In this scenario, our entire observable universe might be just a patch of a much larger reality that is, on the whole, wildly inhomogeneous. We might be living in a neighborhood that is statistically unusual compared to the cosmos at large, a notion that directly violates the cosmological principle's assertion that no place is special. Some of the most thrilling potential explanations venture into truly speculative territory. Could the hemispherical asymmetry be the signature of a pre-inflationary relic, a fossil from the time before the Big Bang? Or perhaps it is evidence of a collision with another universe bubble in the multiverse, an event that would have delivered a tremendous and imbalanced injection of energy to one side of our cosmos, forever breaking its perfect symmetry. The hemispherical asymptoty is more than just another anomaly. It is a direct and confrontational challenge to our most basic assumptions about the universe's structure. It tells us that the cosmos may not be a featureless sea, but might have a topography, a landscape with highlands and lowlands on a scale so vast we can only just perceive its slope. This single finding opens the door to a universe that is far more complex, textured, and strangely directional than we ever thought possible. But just as we're grappling with the unsettling idea of a lopsided universe, the cosmic microwave background confronts us with a mystery that isn't about what is there, but about what isn't. This is the enigma of the missing large-scale correlations, a finding so strange it suggests the universe might have a fundamental size limit, or that our understanding of its infancy is missing a crucial piece of the puzzle. To grasp this concept, let's think about the CMB map not as a picture, but as a vast network of connections. Each hot and cold spot is not an isolated feature. It's linked to others through the physics of the early universe. Scientists study these links using a tool called the angular correlation function. This measures how likely it is that 2 points in the sky, separated by a specific angle, will have similar temperatures. It's a way of quantifying the friendship between different parts of the cosmos. On small scales, we see exactly what our standard cosmological model predicts: a rich web of correlations where points that are close together tend to have similar temperatures, a direct result of sound waves rippling through the primordial plasma. The model also makes a clear prediction for the very largest scales, angles greater than 60 degrees on the sky. These enormous separations correspond to the fundamental size of the universe when it was just 380,000 years old, a scale known as the cosmic horizon at recombination. The theory states that there should still be detectable correlations across these vast distances, faint echoes of quantum fluctuations that were stretched to cosmic proportions during inflation. These large-scale correlations are a vital prediction. They are the signature of a coherent beginning, a universe that was once small enough for every part to be in causal contact. However, when astronomers meticulously measured this angular correlation function, they made a baffling discovery. At angles larger than 60 degrees, the correlation doesn't just get weaker as expected, it drops off a cliff, plummeting to nearly zero. It's as if the universe's largest structures simply refuse to talk to each other. This isn't a minor discrepancy. It's a dramatic absence of signal where our most fundamental theories insist one must exist. The vast, opposing hemispheres of the cosmos appear to be complete strangers with no shared history whatsoever. This missing handshake on the grandest of scales is a deep and persistent problem. So, what could possibly explain this cosmic silence? One of the most straightforward, yet profoundly unsettling, possibilities is that the universe is simply smaller than we think. Our observable universe is a sphere limited by the distance light has traveled since the Big Bang, but the entire universe could be much larger or even infinite. However, if the entire cosmos were actually finite and relatively small, with a complex overall shape like a hall of mirrors, then there would be a natural maximum scale for correlations. Light would have wrapped around this smaller universe, creating patterns only up to a certain size and leaving the larger angles empty. In this scenario, the lack of large-scale correlations would be a direct clue that we are living in a compact universe, a cosmic room with invisible walls on a scale we can barely conceive. The other, perhaps more likely, explanation points to a gap in our understanding of physics itself. The leading theory, cosmic inflation, is brilliant at explaining the universe's uniformity and flatness, but some models of inflation naturally produce a suppression of power on the very largest scales. It's possible that the specific dynamics of the inflationary field, the engine that drove the hyper-expansion, somehow turned off the correlations at these extreme angles. Perhaps inflation didn't last quite long enough to imprint its signature on the absolute largest scales, or maybe the quantum fluctuations that were stretched into existence had a characteristic scale themselves. This would mean that the missing correlations are not a flaw in the universe, but a vital clue to the precise nature of inflation, a fingerprint of the mechanism that created everything we see. There's also a more radical interpretation that we are seeing the effects of pre-Big Bang physics. Some theories suggest that our universe was born from a collision of higher dimensional membranes or emerged from a previous cosmological phase. These models can naturally lead to a cut-off in the spectrum of fluctuations, effectively erasing the correlations on scales larger than the event that created our universe. The eerie silence on the largest scales would then be an echo from the time before time, a relic of the ultimate origin event itself. The absence of signal becomes the most important signal of all, a window into the conditions that gave birth to the cosmos. This mystery reminds us that sometimes the most powerful statements the universe makes are the things it leaves unsaid. After confronting the profound silence of the missing large-scale correlations, our investigation takes a turn toward a force that is both familiar and deeply mysterious: magnetism. You experience it every time a fridge magnet holds up a photo or a compass needle points north. But what if this fundamental force didn't just emerge later in the universe's history? What if it was there at the very beginning, woven into the fabric of the cosmos in its first moments? This is the compelling mystery of the primordial magnetic fields, and the cosmic microwave background may hold the key to proving their existence. The magnetic fields we observe today, threading through galaxies and galaxy clusters, are incredibly powerful. They guide the flow of cosmic gas, shape the formation of stars, and propel high-energy particles across unimaginable distances. For a long time, astronomers assumed these fields were generated later in cosmic history through dynamic processes, like the churning of gas within galaxies or the turbulent motion of galaxy clusters, a theory known as the dynamo effect. But there's a growing problem with this idea. We are now detecting coherent magnetic fields in the very earliest galaxies and in the vast, pristine filaments of gas between them, regions so young and undeveloped that there simply hasn't been enough time for a dynamo to amplify a weak seed field into the strengths we observe. It's like walking into a factory that has just been built and finding a fully operational, complex machine already running at full speed. The machine is there, but there's no clear explanation for how it was built so quickly. This has led scientists to a radical alternative. Perhaps the magnetic fields didn't form late but were present from the very start. The theory proposes that in the extreme energy and chaos of the universe's first nanosecond, during those first frantic moments of inflation or the phase transitions that followed, the conditions were perfect for the spontaneous creation of magnetic fields on a cosmic scale. Quantum fluctuations, those tiny wrinkles in spacetime that inflation stretched into galaxies, could have also generated minuscule electromagnetic currents. As the universe expanded at a breathtaking rate, these feeble fields would have been stretched and frozen into the very fabric of spacetime, becoming what we call primordial magnetic fields. They wouldn't be the product of later astrophysical engines. They would be a foundational feature of the universe itself, a relic as ancient as the CMB. The challenge, of course, is proving it. We can't go back in time to measure them, but we might not have to, because if they exist, these primordial fields would have left a unique and lasting imprint on the oldest light we can see. This is where the polarization of the cosmic microwave background becomes our most powerful detective. The CMB light is polarized in specific patterns, much like light reflecting off the surface of a lake. Scientists carefully study these patterns, categorizing them into two main types, E modes and B modes. E modes are curling patterns that are primarily created by density waves in the primordial plasma, the ordinary stuff of the early universe. B modes, on the other hand, are a twisting, curling pattern that can be created by two incredible sources: the gravitational waves from inflation, which we discussed earlier, and the bending of light by gravitational lensing as it travels across the universe. But there is a third potential creator of specific B-mode patterns: primordial magnetic fields. A magnetic field permeating the early plasma would have exerted a force on the charged particles within it. This would have generated unique, vortical motions, little whirlpools and eddies in the hot soup of the universe. These motions would have imprinted a very specific twist on the polarization of the CMB light, a distinctive fingerprint that is different from the B modes created by inflation or lensing. Finding this particular signature would be like discovering the artist's initial sketch hidden beneath the final painting, a direct glimpse into the forces at play in the universe's first instant. The implications of such a discovery would be nothing short of revolutionary. It would mean that magnetism is not an emergent property of the cosmos, but a fundamental one, as intrinsic to its nature as gravity or matter. It would completely reshape our understanding of cosmic evolution, providing a pre-existing framework that guided the formation of the first structures from the very beginning. Instead of galaxies creating their own magnetic fields, they would have simply grown around these ancient cosmic skeletons. Furthermore, confirming the existence of primordial fields would provide crucial, indirect evidence for the physics of the ultra-early universe, offering a new window into the energy scales and phase transitions that occurred long before the CMB was emitted. The search for this magnetic fingerprint is now a primary goal for next-generation observatories, a hunt for a ghostly force that may have been shaping the destiny of the universe since the moment it was born. And just as we follow the ghostly trails of primordial magnetism, our journey brings us to the heart of a modern scientific debate so intense it could determine the fate of our most cherished theory of the cosmos. This is the controversy surrounding the tensor-to-scalar ratio, a seemingly dry statistical parameter that has become the most sought-after number in all of cosmology, a numerical key that could either unlock the secrets of cosmic inflation or send theorists back to their drawing boards. To understand what's at stake, we need to grasp what this ratio actually represents. It boils down to a simple but profound comparison of two types of wrinkles in the fabric of the early universe. The first type, known as scalar perturbations, are the straightforward density waves, the compressions and rarefactions in the primordial plasma that eventually collapsed under gravity to form all the galaxies, stars, and planets we see today. They are the fundamental seeds of all structure. The second type, tensor perturbations, are something entirely different and far more exotic. These are ripples in the very fabric of space-time itself. Primordial gravitational waves generated by the violent, explosive energy of cosmic inflation. Think of the infant universe as a pond. The scalar perturbations are the ripples on the water's surface. The tensor perturbations are the vibrations shaking the entire pond itself. The tensor to scalar ratio, often denoted as R, is the measure of the relative strength of these two signals. A high value for R would mean that the gravitational wave signal is strong, telling us that inflation was an incredibly energetic, violent process. A low value, or even zero, would suggest a much gentler, slower rolling event. But the ultimate prize is simply detecting a non-zero value at all. Finding the clear fingerprint of these primordial gravitational waves in the CMB would be the smoking gun, the direct, incontrovertible evidence that cosmic inflation truly happened. It would be our first direct glimpse into the energy scales of the universe, a trillionth of a second after the Big Bang. The hunt for this signal focuses on a specific feature in the CMB's polarization, the primordial B modes we discussed earlier. These twisting patterns are the unique signature that inflationary gravitational waves would have imprinted on the ancient light. The problem is that this signal is incredibly faint, buried under a mountain of foreground noise and other effects. Detecting it is like trying to hear a single, specific whisper in a roaring hurricane. This immense challenge has led to a situation where different experiments, using different technologies and observing different parts of the sky, are arriving at starkly different conclusions, creating a rift in the cosmological community. On one side of this great divide is the BICEP collaboration. Operating from the incredibly dry and clear air of the South Pole, the BICEP 2 telescope made global headlines in 2014 with an announcement that sent shockwaves through the world of science. They reported they had detected the telltale swirl of primordial B modes, implying a surprisingly high tensor to scalar ratio. For a brief, exhilarating moment, it seemed we had finally found the proof for inflation. But the triumph was short-lived. Further joint analysis with the Planck satellite revealed that the BICEP team had been fooled. Their signal was not from the dawn of time. It was foreground contamination from interstellar dust within our own Milky Way galaxy, its subtle polarization mimicking the signal they so desperately sought. It was a sobering lesson in humility and the extreme difficulty of this measurement. Subsequent experiments like the Keck array and the more advanced BICEP 3 have continued to observe, pushing their sensitivity to incredible limits. They have not made another definitive detection. Instead, they have consistently reported only upper limits, saying that if the signal is there, it must be smaller than a certain value. Their data suggests that R is very, very small, pointing toward the more gentle models of inflation, but the plot thickens considerably on the other side of the world. At the High Atacama Desert in Chile, another project called the Atacama Cosmology Telescope, or ACT, has been gathering its own data. In 2021, the ACT team released an analysis that once again suggested the possible presence of a gravitational wave background, a signal that would correspond to a higher value of R. They were very cautious, not claiming a discovery, but stating that their data showed a curious excess of power that could be interpreted as the signature of primordial gravitational waves. This result directly contrasts with the increasingly stringent upper limits from the South Pole experiments. So here we are, left with a glaring tension. Two of the world's most sophisticated CMB observatories, looking at the same ancient light but from different vantage points and with different methodologies, seem to be telling two different stories about the birth of the universe. One story suggests a powerful, high-energy inflationary event that should have left a strong gravitational wave imprint. The other suggests a much quieter, more subtle beginning, with any gravitational wave signal being too faint to yet discern. This isn't just an academic disagreement, it's a fundamental uncertainty at the core of our cosmic origin story. The resolution will come from a new generation of experiments already underway. Projects like the Simons Observatory and the colossal CMB-S4 project, which will deploy hundreds of thousands of detectors, are designed to be so sensitive that they will finally settle the debate. They will map the polarization of the CMB with such exquisite detail that they can unequivocally distinguish the faint whisper of inflation from the confounding roar of galactic dust. They will either find the signal and confirm our grandest theory, or they will push the upper limits for R so low that they will effectively rule out a wide swath of the most popular inflationary models, forcing a dramatic and thrilling rethink of what happened in the very first moment of everything. The tensor-to-scalar ratio is more than a number. It is the universe's own verdict on its explosive birth, and we are still waiting for the final word. Just as we grapple with the physics of the universe's birth, we're confronted by a crisis unfolding in the present day, a fundamental disagreement over the very speed at which the cosmos is growing around us. This is the Hubble constant tension, and it's not just a minor calibration dispute between astronomers, it's a full-blown rift that threatens to crack the foundation of our standard model of cosmology. The Hubble constant, denoted as H0, is one of the most critical numbers in all of cosmology. It quantifies the current rate of the universe's expansion. Think of it as the current speedometer reading for the entire cosmos, telling us how fast galaxies are receding from us for every megaparsec of distance. Knowing this value precisely is essential because it tells us the age of the universe, its ultimate fate, and it's the cornerstone for measuring distances to faraway galaxies. For decades, astronomers have worked to pin down this number with ever greater accuracy, expecting that different methods would eventually converge on a single, universal truth. But that's not what's happening. Instead, we have two powerful, precise, and utterly confident methodologies that are giving us two different, incompatible answers. On one side of this divide, we have what's known as the local distance ladder measurement. This is a meticulous, step-by-step process that builds a cosmic ruler out into the universe. It starts with incredibly precise parallax measurements from missions like Gaia to nail down distances to nearby stars. We then use those stars to calibrate the brightness of certain types of variable stars called Cepheids, whose pulsation period is directly related to their intrinsic brightness. We find these Cepheids in nearby galaxies and then use them to calibrate the ultimate cosmic mile markers, type Ia supernova. These supernovae are so brilliantly consistent in their peak brightness that they can be seen and used to measure distances to galaxies billions of light years away. By measuring how fast these distant supernovae are moving away from us, their redshift, and comparing it to their distance, we get a direct measurement of the Hubble constant. This entire chain of evidence, painstakingly assembled over years, points to an expansion rate of about 73 kilometers per second per megaparsec. Now enter the cosmic microwave background and the incredibly precise data from the Planck satellite. This approach is completely different. It doesn't measure the universe's expansion today. Instead, it looks back to the infant universe, to that snapshot of the CMB from when the universe was just 380,000 years old. The detailed patterns of hot and cold spots in this ancient light are a frozen record of the physics at that time. Scientists can take this snapshot and run the cosmological model forward in time, using our exquisitely tuned understanding of dark matter, dark energy, and the laws of physics to predict what the expansion rate should be today. This is a model-dependent measurement, but it's based on the standard model of cosmology that has been spectacularly successful at explaining so much of what we see. And the Planck data gives us a very firm prediction, 67.4 kilometers per second per megaparsec. The difference between 73 and 67.4 might seem small, but in the world of precision cosmology, it's a yawning chasm. The error bars on each measurement, representing their uncertainty, have gotten so small that they no longer overlap. There is now less than a 1 in a million chance that this discrepancy is just a random fluke. We are faced with a stark either-or scenario. Either one of these methods has a hidden systematic error that we haven't been able to find despite years of searching, or our standard cosmological model, the lambda-cold dark matter model, is incomplete. We might be missing a crucial piece of physics. The possibility of a systematic error is always the first place scientists look. Teams have cross-checked the local distance ladder using different calibration stars and even different types of supernova, but the higher value persists. The Planck team has scrutinized their data for any possible contamination or processing artifacts, and their lower value remains rock solid. Each camp has checked and rechecked their work, and both are convinced of their results. This stubborn refusal of the numbers to agree is what transforms a simple discrepancy into a genuine tension, a pulling apart of our understanding. This is why the physics community is so electrified. If it's not an error, then we are on the verge of something monumental, new physics. What could this new physics be? The possibilities are as thrilling as they are profound. It could be that dark energy, the mysterious force accelerating the expansion, is not constant as we've assumed, but is dynamic, changing in strength over time. Perhaps there is a new, previously unknown type of dark radiation that existed in the early universe, altering how we interpret the CMB. Some theories even suggest the properties of dark matter itself might be more complex than we thought. Or, most intriguingly, it could hint that our gravitational theory, Einstein's general relativity, needs modification on the largest cosmic scales. The Hubble constant tension is more than a scientific debate. It's a live wire running through the heart of modern cosmology. It represents the thrilling moment when observation refuses to conform to theory, forcing us to look deeper and think bigger. It's a reminder that the universe still holds profound surprises, and that the most fundamental numbers we use to describe reality may still be just beyond our grasp, waiting for a new generation of thinkers to unlock their secret. Yet, just as we measure the universe's current expansion and its very first light, we find a mystery written not in the distant cosmos, but in the ancient stars right here in our own galactic neighborhood. This is the lithium problem, a quiet but persistent puzzle that emerges directly from the pristine conditions of the Big Bang and challenges the very core of our understanding of nuclear physics in the universe's first minutes. The story begins with a process called Big Bang nucleosynthesis, or BBN. This is the narrative of the universe's very first atoms. For a brief window of time, between about 1 second and 20 minutes after the Big Bang, the entire cosmos was a perfect, seething nuclear furnace. The temperature and density were just right for nuclear reactions to fuse the primordial soup of protons and neutrons into the first light elements, primarily hydrogen, a good amount of helium, and trace amounts of deuterium, helium-3, and lithium. This was the universe's first and largest ever nuclear reaction, and it set the chemical composition for everything that would follow. The amounts of each element produced in this frantic few minutes are not guesswork. They are precise predictions made by our standard cosmological model. The single most important parameter for these predictions is the density of ordinary matter baryons in the early universe. And this is where the cosmic microwave background provides the crucial key. The detailed map of the CMB from Planck gives us an exquisitely precise measurement of that primordial baryon density. The patterns of fluctuations we see are a direct reflection of how much normal matter was present to interact with the light. It's a fixed number, a fundamental input to our models. When we plug this number, derived from the infant universe's baby picture, into our equations for Big Bang nucleosynthesis, the calculations work spectacularly well for most elements. The predicted abundance of deuterium, for instance, matches almost perfectly with the amounts we observe in the most ancient, pristine clouds of gas in the universe. The predicted amount of helium-4 is also spot on. This incredible agreement is one of the towering triumphs of modern cosmology, confirming our basic story of the hot Big Bang. But there is one glaring, stubborn exception: lithium-7. The theory, armed with the precise data from the CMB, confidently predicts that a certain amount of this isotope should have been forged in those first moments. When we then go out and look for this lithium in the oldest stars in the halo of our Milky Way stars that formed from gas that was nearly uncontaminated by later generations of element-producing stars, we find a discrepancy that has persisted for decades. The observed amount of lithium-7 in these ancient stellar atmospheres is only about 1/3 of what our best models say it should be. It's not a small margin of error, it's off by a factor of 3. The universe's first nuclear reactor seems to have somehow failed to produce its full quota of this one particular element, and we are left with a conspicuous absence. This isn't just a minor accounting error, it's a fundamental problem. The BBN calculation is a straightforward chain of nuclear reactions, a well-understood sequence governed by known physics. If the input, the baryon density from the CMB, is correct, and the outputs for other elements match, then the problem must lie somewhere in the specific nuclear reaction pathways that lead to lithium-7. Perhaps there is a nuclear physics rate we have wrong, maybe a key reaction cross-section. The probability that two nuclei will interact and fuse is significantly different in the extreme conditions of the early universe than what we measure in our laboratories on Earth. Some physicists have proposed the existence of unknown particles, like certain types of neutrinos, that could have been present during BBN and altered the delicate balance of reactions, selectively destroying lithium as it formed. Another possibility is that our understanding of the stellar astrophysics itself is flawed. Perhaps these ancient stars have internal processes we don't fully understand that slowly destroy lithium over their multi-billion-year lifetimes, dredging the depleted material to the surface where we observe it. Or maybe the primordial lithium was somehow diluted or processed in the gas clouds that existed before the first stars even formed. Yet, despite extensive searches, no single solution has managed to fully resolve the problem without breaking the beautiful agreement we have for all the other elements. The lithium problem stands as a quiet but powerful reminder that even our most successful models may still be missing a piece of the puzzle, a subtle piece of physics that operated for just a few minutes in the entire history of the cosmos, leaving its mark only in the lack of a single element in the oldest stars we can find. Yet, even as we search for answers within the bounds of our observable universe, the cosmic microwave background appears to be pointing a ghostly finger towards something far beyond our cosmological horizon. This is the deeply puzzling and controversial mystery of the dark flow, a finding that suggests our entire local universe might be caught in a cosmic current, pulled by a gravitational source so immense and so distant that it lies outside everything we can possibly see. The story begins with a subtle but powerful observational technique called the kinetic Sunyaev-Zeldovich effect. To understand this, picture a massive cluster of galaxies. It's filled with incredibly hot gas, and swimming through this gas are countless electrons. Now, imagine the ancient light from the cosmic microwave background passing through this cluster on its 14-billion-year journey to our telescopes. As those CMB photons collide with the fast-moving electrons in the hot gas, something fascinating happens. The photons get a slight energy boost. If the cluster is moving toward us, the collisions make the CMB light appear a tiny bit warmer in that direction. If the cluster is moving away, the light appears a tiny bit cooler. It's a minuscule effect, but by carefully measuring these subtle temperature shifts in the CMB around thousands of galaxy clusters, astronomers can essentially map the bulk motion of these enormous structures through space. They can measure not just how individual galaxies are moving, but how entire clusters, each containing thousands of galaxies, are streaming together. When a team of scientists led by Alexander Kashlinsky applied this technique to a huge catalog of clusters, they expected to see a random cosmic dance. The standard model of cosmology tells us that on the largest scales, the universe is homogeneous and isotropic. There should be no preferred direction for motion. The expansion of the universe should be the dominant, smooth force, with any other motions being small, local, and random. But the data told a completely different and shocking story. The analysis revealed that a staggering number of these massive clusters, thousands of them, were not moving randomly at all. Instead, they were all streaming in the same direction at astonishing speeds of nearly 1,000 kilometers per second, a motion that is directly aligned with the mysterious hemispherical asymmetry we discussed earlier. This coherent, large-scale bulk motion is what was dubbed the dark flow. The name itself is a clue to its profundity. Dark because its cause is completely unknown and invisible, just like dark matter and dark energy. Flow because it implies a directed, river-like movement of matter on a scale that is almost incomprehensible. The most baffling part is the scale of this motion. These clusters are so far apart that they should be completely beyond each other's gravitational influence. There is no known concentration of mass within our observable universe, no supercluster, no immense wall of galaxies that is large enough or powerful enough to be pulling all of this matter in one unified direction. The gravitational source for this flow would have to be truly colossal, far exceeding the pull of the Great Attractor or any other structure we've mapped. This is where the mystery becomes truly profound, pushing the boundaries of known physics. The most startling explanation proposed is that the source of this gravitational pull lies beyond the edge of our observable universe. According to our standard cosmology, the universe we can see is limited by the distance light has traveled since the Big Bang. But the entire cosmos is likely much larger than this observable bubble. The dark flow could be evidence that there is an enormous mass concentration, a density fluctuation on a scale we can scarcely imagine residing in this unobservable territory. Its gravitational influence would be reaching across the void, tugging on everything in our local universe like a hidden magnet. This idea is both thrilling and unsettling, as it suggests that our cosmic environment might be far from typical and that our entire observable universe is just a small part of a much larger and more structured cosmos. Naturally, a claim this extraordinary faces intense scrutiny and skepticism. The primary counter-argument is that the detected signal is not a real flow at all, but a systematic error introduced during the incredibly complex process of data analysis. Detecting the kinetic Sunyaev-Zeldovich effect requires first meticulously subtracting all other foreground signals: the light from our own galaxy, the thermal Sunyaev-Zeldovich effect from the cluster's own hot gas, and countless other sources of noise. Critics argue that even a tiny residual imperfection in this cleaning process could create the illusion of a coordinated flow where none exists. Subsequent studies using data from the Planck satellite have failed to confirm the original dark flow detection with the same significance, adding fuel to the debate and leaving the cosmological community deeply divided. Whether the dark flow is ultimately confirmed as a real phenomenon or dismissed as a measurement artifact, its very proposal has already served a crucial purpose. It has forced us to confront the limits of our knowledge and to ask audacious questions about what might lie beyond our cosmological horizon. It challenges the comforting assumption of isotropy and dares us to consider that our universe might not be a self-contained island, but part of a vast archipelago whose other shores we can never directly see, yet whose presence we might just be able to feel through the ghostly tug on everything we know. Yet, even as we chart the universe's expansion rate and its ancient elemental fingerprints, the cosmic microwave background is hinting at an energy crisis that occurred not in the deep future, but in the cosmos's very first moments. This is the early dark energy problem, a tantalizing clue that the mysterious force accelerating the universe today might have had a wild, energetic counterpart that briefly flared into existence at the dawn of time, leaving its subtle signature in the ancient light. To understand this, we need to revisit the standard story of dark energy. In our current model, dark energy is the dominant force in the universe today, responsible for its accelerating expansion. But for most of cosmic history, it was a negligible whisper. In the early universe, the density of matter and radiation was so overwhelming that their gravitational pull dominated, slowing the expansion down. Dark energy only became significant billions of years later, as the universe expanded and diluted, allowing this mysterious repulsive force to take over. This timeline is a core part of our standard cosmological model, and it fits a vast array of data beautifully. But when we look at the most precise measurements of the CMB, a small crack appears in this elegant narrative. The evidence comes from a specific feature in the CMB's power spectrum, the detailed chart of temperature fluctuations across the sky. The precise size and spacing of these hot and cold spots are exquisitely sensitive to the contents and expansion history of the early universe. It's like a cosmic barcode that we can scan to read out the exact amounts of dark matter, ordinary matter, and the timing of key events. When scientists analyzed the Planck data with the standard model, they found an excellent fit, but not a perfect one. There remains a persistent, subtle tension in how the model accounts for the sound horizon at the time the CMB was emitted. This is the distance that sound waves could travel in the plasma before the universe became transparent. The data seems to suggest this horizon is just a little bit smaller than our standard model predicts it should be. How do you make that sound horizon smaller? You make the universe expand a little bit faster during those first few 100,000 years. If the expansion was slightly more vigorous, the sound waves would have had less time to travel before they were frozen into the CMB, creating a slightly smaller pattern on the sky. This is where the idea of early dark energy comes in. It proposes that in addition to the dark energy we know today, there was another, transient form of energy that existed only in the universe's infancy. This wouldn't be the same constant energy. Think of it as a burst of extra push, a short-lived, exotic energy field that provided an additional source of repulsion, giving the expansion a brief boost during that critical first act before fading away into irrelevance. This is a radical proposal. It suggests that dark energy isn't a single, monolithic entity, but that there could be different phases or types of it throughout cosmic history. This early dark energy would have operated like a cosmic afterburner, kicking in for a short period to accelerate the expansion just enough to leave the specific signature we might be seeing in the CMB. Intriguingly, this very same modification could also help ease the Hubble tension. A faster expansion in the early universe would naturally lead to a higher predicted expansion rate today, potentially bridging the gap between the CMB's 67 and the local measurement of 73. The implications of this are staggering. If proven, it would mean our universe underwent not one, but two distinct phases of acceleration. A brief, powerful burst at the very beginning from this early dark energy, and the slow, steady takeover of the dark energy we see today. It would revolutionize our understanding of the vacuum of space itself, suggesting it is far more dynamic and complex than we ever imagined, capable of cycling through different energy states. The search for confirmation is now a major driving force in cosmology. The next generation of CMB experiments and large-scale galaxy surveys will look for the unique fingerprint of this early boost in expansion. They will measure the clustering of galaxies at different eras, cross-checking the expansion history with unprecedented precision. The early dark energy hypothesis reminds us that the universe's first chapters may still hold surprises that rewrite the later ones. It turns the story of cosmic acceleration from a simple tale of a late-arriving hero into a potential epic with multiple acts, a narrative where the forces shaping our cosmos are more fluid and mysterious than we dared to dream. After exploring the universe's earliest moments and its mysterious expansion, we now journey forward in cosmic time to an era often called the universe's second dawn. This dramatic period, known as the epoch of reionization, represents one of the most profound transitions in cosmic history, and the story of how we're piecing it together and why it remains deeply puzzling is written in the polarized light of the cosmic microwave background. To understand reionization, we need to rewind to the universe's infancy just after the CMB was released. For nearly 400,000 years, the cosmos was a dark, neutral fog of hydrogen gas. There were no stars, no galaxies, and no sources of light. This period is poetically known as the Cosmic Dark Ages. Then, something revolutionary happened. The first stars and galaxies began to flicker on, flooding the universe with its first starlight. These weren't like the stars we see today. They were behemoths, hundreds of times more massive than our sun, burning ferociously hot and bright before exploding in spectacular supernova. Their intense ultraviolet radiation began to tear apart the neutral hydrogen atoms that filled the cosmos, splitting them back into their constituent protons and electrons, a process called ionization. Think of it like a cosmic sunrise happening in slow motion, where the morning light doesn't just illuminate the landscape but fundamentally changes the very air itself, burning away a pervasive fog to create a clear, transparent sky. This was reionization, the universe waking up, transforming from a neutral fog into the ionized, transparent plasma that fills intergalactic space today. But how do we possibly study an event that happened over 13 billion years ago? We can't see those first stars directly. They are far too faint and distant. This is where the cosmic microwave background once again becomes our ultimate time machine. While the CMB's temperature map shows us the universe at 380,000 years old, its polarization carries an echo of this much later event. As the first starlight began to ionize the hydrogen gas, those newly freed electrons were once again able to scatter the CMB photons. But this time, the scattering wasn't happening in a hot, dense plasma. It was occurring as the light passed through these growing, patchy bubbles of ionization. This rescattering imprinted a unique, large-scale pattern on the polarization of the CMB, specifically in what we call the E-mode polarization. It's a faint but detectable ghostly signature of that second dawn, a shadow cast upon the ancient light by the very first structures in the universe. By meticulously analyzing this E-mode polarization pattern, particularly its power on the very largest angular scales, cosmologists can essentially carbon date the epoch of reionization. The data from the Planck satellite provides a crucial measurement, the optical depth to Thomson scattering, denoted by the Greek letter tau. This number tells us the total amount of scattering that occurred along the path of the CMB light, and it is directly tied to when and how quickly reionization happened. The Planck measurement points to a universe that was half reionized by the time it was around 700 million years old, and was fully transparent by the time it reached 1 billion years. This gives us a rough timeline for this cosmic transformation. Here is where the mystery, the reionization puzzle, truly begins. This timeline derived from the CMB doesn't quite match the story being told by our most powerful astronomical observatories. The Hubble Space Telescope and now the James Webb Space Telescope peer back in time to directly observe the galaxies that existed during this epoch. They are conducting deep field surveys, counting the number of galaxies, measuring their brightness, and estimating how much ionizing ultraviolet radiation they were producing. The problem is, when astronomers add up all the light from all the galaxies they can see at that time, there doesn't seem to be enough juice to power the cosmic reionization process as quickly as the CMB suggests. It's like trying to heat a massive swimming pool with a handful of candles. The energy source appears insufficient for the task. This discrepancy has launched a fierce scientific detective story. Are we simply missing a huge population of faint early galaxies? The James Webb Space Telescope was built in part to find exactly these tiny, dim galaxies that Hubble couldn't see. Its early data is already revealing a universe that was brimming with more galaxies earlier than we predicted. Yet the puzzle persists. Perhaps the first stars were far more efficient at producing ionizing radiation than we thought, or maybe there were other, more exotic sources of energy at play. Some theories suggest that material falling onto supermassive black holes in the cores of these early galaxies, objects known as mini-quasars, could have provided a significant boost of ultraviolet light. Others wonder if the physics of how radiation escapes from these primeval galaxies is different, that perhaps their low metal content and simple structure allowed far more ionizing photons to stream out into the cosmos than is possible from modern galaxies. The duration of reionization is another part of the enigma. Did it happen rapidly, a sharp and violent transition, or was it a slow and gradual process? The CMB polarization hints at a relatively quick event, but some astrophysical models suggest it may have been more drawn out. The answer to this question holds the key to understanding the nature of those first sources of light. A rapid reionization would point to a dominant population of incredibly bright, massive stars and galaxies appearing in a coordinated burst. A slower process would allow for a more gradual buildup of smaller sources. The truth likely lies somewhere in between, a complex tapestry of different objects all contributing to clearing the cosmic fog. The reionization puzzle is more than just an argument over dates and energy budgets. It strikes at the heart of how we understand the formation of the very first structures in the universe. It forces us to question how galaxies are born and how they evolve, and it challenges our senses of the cosmic population during this critical era. Resolving this tension is a primary goal for current and future observatories. By combining the pristine, all-sky view from the CMB with the deep, focused gaze of telescopes like JWST, we are slowly piecing together a complete narrative of this cosmic renaissance. We are closing in on a moment-by-moment account of how the lights came on, ending the dark ages and setting the stage for the rich, structured universe of galaxies we inhabit today. This puzzle reminds us that even an event as monumental as the birth of starlight leaves behind a complex and fragmented record, one that requires every tool at our disposal to decode. But just as we piece together the story of the universe's reawakening, we must turn our attention to a ghostly population of particles that flowed through that primordial plasma, subtly influencing the cosmos without ever leaving a direct mark on the light. This is the mystery of the neutrino mass constraint, a profound example of how the cosmic microwave background acts as a giant particle physics laboratory, placing some of the tightest limits ever on the most elusive particles known to science. Neutrinos are the phantoms of the subatomic world. Trillions of them are passing through your body every second, yet they interact with matter so rarely that they can traverse light years of lead without a single collision. They were produced in staggering numbers in the Big Bang, and they decoupled from the rest of the universe just 1 second after it began, flooding the cosmos and streaming freely through everything. For decades, we knew they had to have some mass thanks to the phenomenon of neutrino oscillation, where they change between different types as they travel. But pinning down exactly how much mass they have has been one of the great challenges of modern physics. The answer is not just a number in a table. It holds the key to understanding physics beyond the standard model and could reshape our picture of how large-scale structure formed in the universe. This is where the cosmic microwave background becomes an unexpected but incredibly powerful scale. While neutrinos were too elusive to scatter CMB photons directly, their collective gravitational influence left a clear and lasting imprint on the patterns we see. The key lies in how these particles behaved as the universe evolved. In the very early, dense universe, even neutrinos were moving relativistically at speeds close to light. In this state, they act like a form of radiation, and their intense, fast motion has a specific effect. It smooths out matter fluctuations. They can freely stream out of regions that are trying to collapse under gravity, washing out the very smallest ripples in the matter distribution. Think of it like trying to build a sandcastle with very fine, dry sand. The grains simply won't clump together on a small scale. As the universe expanded and cooled, however, neutrinos eventually slowed down. Once their kinetic energy dropped below their rest mass energy, they transitioned from behaving like radiation to behaving like matter. This crucial shift meant they stopped smoothing out structure and actually started to contribute to the gravitational collapse that forms galaxies and clusters. The timing of this transition and the amount of smoothing that occurred before it is exquisitely sensitive to one thing: the sum of the masses of all three neutrino types. Heavier neutrinos would have made this transition earlier. They would have stopped their free-streaming smoothing effect sooner, allowing more small-scale structure to form. Lighter neutrinos would have kept streaming for longer, suppressing more of the small-scale clumping. This is the brilliant detective work cosmologists perform. They take the incredibly detailed map of the CMB's temperature and polarization fluctuations, a snapshot of the universe's structure at age 380,000 years, and combine it with maps of the universe's structure today from massive galaxy surveys. By comparing the amount of structure on small scales in the ancient universe to the amount we see now, they can measure how much smoothing occurred in between. And that measurement tells them the mass of the neutrinos. The constraints that emerge from this cosmic census are astonishingly precise. The latest data, primarily from the Planck satellite combined with surveys like the Dark Energy Survey and others, tells us that the sum of the masses of the three neutrino flavors must be less than about 0.12 electron volts. To grasp how incredibly small that is, consider that an electron, which itself is a lightweight particle, has a mass of 500,000 electron volts. Neutrinos are at least 4 million times lighter. This extraordinarily tight constraint is a monumental achievement, but it has also created a fascinating and growing tension. While cosmology points to a very low total mass, certain terrestrial experiments designed to measure the absolute mass of neutrinos directly, most notably the Catron experiment, are inching toward a range that might be higher. Catron is designed to measure the mass of the electron neutrino with unparalleled precision by studying the energy spectrum of electrons released in radioactive decay. Its initial results have set an upper limit that is consistent with the cosmological bound, but the experiment is still running, and its ultimate sensitivity could potentially measure a value that starts to push against the limits set by the cosmos. If the eventual measurement from Catron or a next-generation experiment were to land definitively above the cosmological limit, it would trigger a true crisis in physics. It would suggest that something is gravely wrong with our standard model of cosmology, the lambda cold dark matter model. Perhaps dark energy is more complex, or maybe there is an additional, unknown relativistic particle in the early universe that is muddying the waters. Alternatively, it could mean that neutrinos themselves have exotic properties we haven't yet dreamed of, perhaps interacting with each other or with dark matter in ways that completely alter their cosmic evolution. The hunt for the neutrino's mass is more than just an academic exercise to fill in a missing datum. These tiny masses could have outsized consequences for the universe's fate. Even a mass as small as 0.1 electron volts per neutrino means there are so many of them that their combined gravitational pull could influence the universe's expansion rate on the largest scales. Furthermore, pinning down their mass is a direct portal to physics at energy scales so high we could never hope to reach them with a particle accelerator on Earth. The fact that we can use the entire cosmos as a lab to probe these questions is a testament to the incredible power of modern cosmology, turning the oldest light in the universe into a precise tool for weighing the lightest particles. After charting the ghostly influence of neutrinos, we arrive at a mystery that strikes at the very geometry of existence, a debate over the fundamental shape of reality that has been reignited by the universe's own baby picture. This is the curvature controversy, a high-stakes scientific disagreement over whether the cosmos is perfectly flat or if it holds a subtle but profound curve. For decades, the prevailing narrative, strongly supported by earlier CMB data, has been one of flatness. The spectacular success of cosmic inflation as a theory seemed to predict this outcome. The idea was that no matter how the universe began, that period of hyper-fast expansion would have stretched the fabric of space-time so dramatically that any initial curvature would have been ironed out, leaving behind a universe with Euclidean geometry. The initial data from missions like WMAP seemed to confirm this beautifully, showing a universe consistent with flatness. The Planck satellite's first major data release in 2013 appeared to put the final nail in the coffin, measuring the density parameter omega to be 1.0008 plus or minus 0.0019. In simpler terms, the universe was measured to be flat to within a razor-thin margin of just 0.2%. This was hailed as a monumental confirmation of the Standard Model. The case seemed closed, but science is a process of ever deeper inquiry, and as the Planck team continued to analyze their full dataset with more sophisticated techniques, a tantalizing whisper of something else emerged from the noise. When they released their final, most comprehensive analysis in 2018, a subset of the data, specifically the measurement of the CMB's gravitational lensing potential, began to tell a slightly different story. This data suggested the universe might not be perfectly flat after all. Instead, it hinted at a positive curvature at a significance level of about 3 sigma. Now, in science, a 3 sigma result means there's roughly a 0.3% chance that the finding is a random fluke. While this falls short of the gold standard 5 sigma threshold required for a definitive discovery, it is far too significant to ignore. It's a persistent signal that refuses to disappear, a wobble in the data that suggests our flat universe might have a slight global bend to it. The implications of such a curvature would be nothing less than revolutionary. A positively curved universe would be finite and closed like the surface of a 4-dimensional sphere. While unimaginably vast, it would not be infinite. This would have cascading consequences for our understanding of everything. For starters, it would challenge the simplest and most popular models of cosmic inflation, which naturally drive the universe toward perfect flatness. If there is curvature, it would mean inflation either didn't last quite long enough to completely flatten our observable patch, or that we need a more complex model of the inflationary field to account for it. Furthermore, a closed universe has a very different ultimate fate. Instead of expanding forever into a cold, empty void, a positively curved cosmos would eventually stop expanding and recollapse in a spectacular Big Crunch, a mirror image of its birth. This wouldn't just change our textbooks, it would fundamentally alter our cosmic destiny. The controversy lies in the tension between different ways of reading the same data. The Planck team itself is careful to present the result as an intriguing hint, not a conclusion. Critics and skeptics point out that the signal for curvature is highly dependent on which specific statistical estimators and data subsets you use. Other analyses of the full Planck data, particularly those combining it with other cosmic probes like the large-scale structure of galaxies, strongly prefer a flat universe and push the curvature signal back down into insignificance. This suggests the 3 sigma hint could be a systematic effect, a subtle glitch in the complex process of untangling the CMB's light from the foreground glow of our own galaxy, or perhaps an unknown source of contamination that subtly mimics the signature of curvature. It's a classic scientific detective story. Is the signal a real clue to a deeper truth, or is it a red herring created by our own imperfect instruments? Resolving this controversy is one of the primary goals for the next generation of cosmological observatories. Projects like the Simons Observatory and CMB-S4 will map the CMB's polarization with orders of magnitude more sensitivity. They will be able to measure the subtle distortions caused by gravitational lensing with such precision that they can directly map the true geometry of the universe. They will either confirm the hint of curvature and force a dramatic rewrite of our cosmic model, or they will finally squash it, cementing the picture of a perfectly flat universe. The curvature controversy is a powerful reminder that even our most foundational assumptions are subject to revision. It shows science not as a collection of settled facts, but as a living, breathing process of questioning, and that the most ancient light in the sky still has the power to surprise us, suggesting that the fabric of reality might be woven with a curve we are only just beginning to perceive. Yet for all the grand questions of geometry and cosmic destiny, some of the most compelling mysteries of the CMB point toward the possible existence of objects that are both incredibly small and unimaginably dense, hidden in the shadows of the early universe. This brings us to the fascinating possibility of primordial black holes, and how the ancient light of the CMB might be the very thing that reveals their shadowy presence or finally rules them out as a major component of the cosmos. When we think of black holes, we typically imagine the stellar mass kind, the remnants of massive stars that have collapsed in a supernova, or the supermassive monsters lurking at the centers of galaxies. But there is another, more speculative class, primordial black holes. These wouldn't be born from dying stars, but from the extreme conditions of the Big Bang itself. The theory suggests that in the first chaotic second of the universe, regions of space that were exceptionally dense could have collapsed under their own gravity directly into black holes. Their masses wouldn't be tied to the life cycle of a star. They could be almost anything from lighter than an asteroid to heavier than 1,000 suns. For decades, primordial black holes have been a compelling candidate to explain the universe's most persistent mystery, dark matter. After all, if they were numerous enough, these ancient, invisible objects would gravitationally pull on everything around them, just like dark matter is observed to do without emitting any light themselves. The cosmic microwave background becomes our most powerful tool for hunting these phantom objects. The reason is beautifully direct. If a significant portion of the dark matter were made of primordial black holes, they would have left a clear and calculable imprint on the universe's first light. Imagine the early universe just before the CMB was released. It's a hot, dense plasma buzzing with radiation and particles. Now, if you were to sprinkle in a population of black holes, even relatively small ones, they would act like cosmic sinks. Their immense gravity would pull in the surrounding matter and energy, effectively creating cold spots in the plasma. But more importantly, as these black holes draw in material, they would also accrete it. The infalling matter would compress and heat up, emitting radiation, primarily in the form of X-rays. This process would inject a tremendous amount of energy back into the primordial plasma, effectively heating it up. This extra energy input would alter the very physics of how protons and electrons combine to form neutral atoms, potentially delaying the moment of recombination when the universe becomes transparent. A delayed recombination would leave a specific signature on the CMB's power spectrum, subtly changing the size and distribution of the hot and cold spots we observe. Furthermore, this accretion energy would not be perfectly uniform. It would create what are known as spectral distortions in the CMB. The pristine blackbody spectrum of the CMB, that nearly perfect curve of radiation, would be subtly warped by this extra energy injection. We would expect to see specific types of distortions, known as mu distortions and Y distortions, which are like chemical fingerprints left behind by early energy sources. If primordial black holes were abundant enough to be the dark matter, the energy they released through accretion would have created distortions far larger than what we actually observe. The fact that the CMB's spectrum is so incredibly close to a perfect blackbody places extremely tight constraints on this possibility. It essentially rules out a universe where most of the dark matter is made of black holes in a wide range of masses, particularly those between about 1 million and 100 billion times the mass of our Sun. However, the story isn't over. The constraints have interesting windows. The CMB data is less sensitive to very, very small black holes because those would have evaporated away by now due to Hawking radiation, and to very, very large ones because they would be so few in number that their collective accretion would be minimal. This leaves open the tantalizing possibility that primordial black holes could still make up some fraction of the dark matter, perhaps in specific mass ranges. The hunt has now shifted to these windows, with scientists using other observational tools like the gravitational microlensing of stars and the ripples in space-time from gravitational waves to search for them. The CMB has played the role of a ruthless editor, cutting out vast swaths of the possible parameter space for these objects, forcing theorists to refine their models and consider more exotic scenarios. It stands as a testament to the power of this ancient light, that it can not only illuminate the grand structure of the cosmos, but also probe the shadowy existence of its smallest and most elusive hypothetical inhabitants. But as we weigh the gravitational whispers of neutrinos in the modern universe, we must journey back to the very first second of time to uncover a ghostly sea of particles even more ancient and elusive than the cosmic microwave background itself. This is the prediction and the profound indirect evidence for the cosmic neutrino background, a relic radiation that has never been seen directly, yet whose shadowy presence is written indelibly into the very peaks and troughs of the CMB. To understand this, we need to reimagine the universe's first frantic moments, a time even before the protons and neutrons had fully formed. Just 1 second after the Big Bang, the cosmos was a seething, dense soup of fundamental particles and energy, a place where the temperature was an unimaginable 10 billion degrees. In this inferno, neutrinos were born in incredible abundance, constantly interacting with electrons, protons, and neutrons. But as the universe expanded at a breathtaking rate, it cooled just as quickly. Within that single second, a critical threshold was crossed. The universe became too cold and too diffuse for these ghostly particles to continue interacting with matter. In an event known as neutrino decoupling, they effectively went dark, streaming freely across the expanding cosmos, never to significantly interact with anything again. This happened a full 380,000 years before the photons of the CMB were set free. This makes the cosmic neutrino background the oldest fossil in the universe, a snapshot of reality at the 1 second mark. So how can we possibly detect something that is fundamentally undetectable by any conventional means? These relic neutrinos have now cooled to a temperature of just about 1.95 degrees above absolute zero, even colder than the CMB, and they possess so little energy that they could pass through light years of lead without a single collision. We cannot build a trap to catch them. Instead, we must become cosmic detectives, looking for the indirect clues they left behind in the one relic we can see, the cosmic microwave background. The key to this detective work lies in a specific and precise feature of the CMB's power spectrum, the timing and height of its acoustic peaks. Those peaks represent the frozen echoes of sound waves rippling through the early universe's plasma. The precise way those waves oscillated was exquisitely sensitive to the ingredients in the primordial soup. Before neutrinos decoupled, they were a dominant component of the universe, and even after they began their free streaming, they continued to exert a powerful gravitational influence. Their unique behavior acted as a cosmic ingredient that changed the recipe for those sound waves. Because neutrinos move at nearly the speed of light, they don't clump together under gravity like slower-moving dark matter or baryons. Instead, they tend to smooth out matter fluctuations on smaller scales, effectively washing out some of the structure. When scientists model the growth of these sound waves without including a sea of free-streaming neutrinos, their predictions for the CMB power spectrum are off. The peaks, particularly the second and third peaks, appear at the wrong amplitudes and slightly shifted positions compared to what we actually observe. The data from the Planck satellite is so precise that it acts like a cosmic scale. By measuring the exact heights and positions of these acoustic peaks, cosmologists can measure the gravitational pull of this invisible neutrino background. The data doesn't just suggest neutrinos were present, it demands it. The observed power spectrum is impossible to explain without including the specific smoothing effect of the cosmic neutrino background. This is how we know it exists, because the ancient light we can see carries the gravitational fingerprint of the ancient light we cannot. The precision is such that we can even count the number of neutrino species from this effect, confirming the existence of the 3 known flavors and finding no evidence for any additional hypothetical types. The quest now is to move from this compelling indirect evidence to a direct detection, a challenge that pushes the very boundaries of experimental physics. The problem is one of unimaginably faint signal. There are predicted to be about 336 of these relic neutrinos in every cubic centimeter of the universe, which means trillions are passing through you every second. But their energy is so low that they are lost in a sea of more energetic neutrinos from the Sun, nuclear reactors, and other terrestrial sources. The hunt requires a new kind of detector, one that can identify the extremely rare interaction of a cosmic neutrino with an atomic nucleus through a process called coherent neutrino scattering. Next-generation experiments are aiming to use vast arrays of ultra-cold, super-sensitive detectors to perhaps one day hear the faintest echo of all the whisper of a particle that has been traveling, untouched, since the first second of time, finally revealing the universe's oldest secret directly to our hands. Yet for all its spectacular success in solving the horizon and flatness problems, the theory of cosmic inflation presents us with a deeply ironic and frustrating puzzle of its own, a cosmic menu with hundreds of exquisite dishes, but no clear way for us to choose which one represents the true flavor of reality. This is the inflationary model selection problem, and it reveals that while the CMB has confirmed the general idea of inflation beyond a reasonable doubt, it has so far failed to guide us to the specific physical mechanism that drove it. Think of it this way: discovering that cosmic inflation occurred is like hearing a single, powerful chord echo across the universe. That chord is the CMB's stunning uniformity and flatness, the telltale signs that a period of hyper-fast expansion must have happened. But that single chord is consistent with an entire symphony of different musical compositions. Each specific model of inflation is like a different score written for that symphony, each with its own unique melodies, rhythms, and instruments. The problem is that our current CMB observations, as precise as they are, have only allowed us to hear that one opening chord clearly. We are still largely deaf to the intricate variations that would allow us to identify which composer wrote the music. The number of proposed inflationary models is staggering, running into the hundreds. They have poetic and complex names: chaotic inflation, natural inflation, hybrid inflation, Higgs inflation, and more. Each is built on a different potential energy landscape, often involving different types of hypothetical scalar fields called inflatons. Some models predict a violent, high-energy inflation that would have generated powerful primordial gravitational waves, leaving a strong twisting pattern B modes in the CMB polarization. Others describe a much gentler, slower roll process that would produce a much fainter gravitational wave signal. Some models predict significant non-Gaussianities, subtle statistical deviations in the distribution of the hot and cold spots that would indicate more complex interactions during inflation. Others predict perfectly Gaussian, random fluctuations. This is where the CMB data has been both a triumph and a tease. The detailed map from Planck is exquisitely sensitive to these details. It has already been powerful enough to rule out entire classes of the simplest inflationary models. The fact that we have not detected primordial B modes at a high level has pushed aside many of the more dramatic high-energy models. The measured Gaussianity of the fluctuations has constrained another large set, but this process of elimination has left a vast plateau of remaining models that all fit the current data equally well. It's like eliminating every person in a lineup who is obviously too tall or too short. You're left with a large group of suspects who are all roughly the same height, and you need much finer tools to identify the true culprit. The core of the problem is that the CMB is essentially a two-dimensional projection of a three-dimensional universe. It gives us a fantastic map of the consequences of inflation, but it is one step removed from the event itself. The primordial gravitational waves we so desperately seek are the only direct messenger from the inflationary energy scale, and their signal is incredibly faint, buried under foreground contamination from galactic dust and the confounding effects of gravitational lensing. Until we can cleanly measure that signal or find another equally powerful discriminant, we are stuck with a multitude of possibilities. This isn't just an academic exercise. The choice of model has profound implications for our understanding of physics. The energy scale of inflation is directly tied to the tensor-to-scalar ratio R. A high value would place inflation at the scale of grand unification, suggesting a direct link to quantum gravity and perhaps string theory. A low value would push it to much lower energies, potentially making it accessible to physics we might one day probe in particle accelerators. Furthermore, some models of inflation naturally lead to a multiverse, an endless froth of bubble universes, while others do not. We are not just trying to select a model, we are trying to select our universe's origin story and its ultimate context within a wider meta-reality. The way forward lies in a new generation of precision cosmology. Projects like the Simons Observatory and CMB S4 are not just upgrades, they are fundamentally new instruments designed to hear the full symphony of inflation. By mapping the CMB's polarization with unimaginable sensitivity, they will hunt for the faint B-mode signal with a precision that can finally distinguish between the whispering models and the shouting ones. They will also create ultra-high-resolution maps of the CMB's lensing and its subtle non-Gaussianities, providing multiple independent lines of evidence to cross-examine the various inflationary suspects. The inflationary model selection problem is a humbling reminder that answering one set of profound questions often just leads to a deeper, more complex layer of mystery. We have graduated from asking if inflation happened to the much more difficult question of how it happened. The CMB has given us the key to the first door, but we are still fumbling in the lock of the second, searching for the precise turn that will reveal the true engine of creation. And just as the cosmic microwave background gives us a powerful census of the universe's contents, it also acts as a strict referee for how those contents are allowed to behave. This brings us to a subtle but profoundly important set of rules written into the ancient light, the dark matter baryon scattering limits, which tell us that our universe's two dominant ingredients must have been living largely separate lives since the very beginning. We know the cast of characters well by now. On one side, we have baryons, the ordinary matter that makes up everything we can see, from stars and planets to our own bodies. On the other, we have dark matter, the invisible, mysterious substance that outweighs baryons by a factor of 5 to 1, whose gravitational pull is the primary architect of the cosmic web. For the most part, our standard cosmological model treats these two components as ships passing in the night. They feel each other's gravity, which is how dark matter can form halos that pull baryons into galaxies, but they are not thought to interact directly through any other force. They are cosmic strangers, aware of each other's presence but never truly touching. Yet, many theories in physics suggest this might not be the whole story. Could dark matter particles occasionally bounce off protons and neutrons like billiard balls colliding? Could there be a new, weak force that mediates a subtle interaction between the visible and invisible worlds? Such interactions aren't just wild speculation. They are predicted by various theoretical models attempting to explain the nature of dark matter, particularly the idea of self-interacting or communicating dark matter. If such interactions did occur, even very rarely, they would have left a clear and calculable fingerprint on the cosmic microwave background. The patterns of hot and cold spots are exquisitely sensitive to any process that transfers energy or momentum between different components of the cosmic fluid. Imagine the early universe as a vast hot soup. The baryons, protons, and electrons are tightly coupled to the light, constantly scattering photons and creating pressure that resists gravity's pull. The dark matter, unaffected by light, simply clumps together under its own gravity. Now, introduce even a tiny amount of scattering between dark matter particles and baryons. This interaction would create a kind of friction. As the dark matter tries to collapse into its own gravitational wells, it would drag the baryonic plasma along with it. Conversely, the pressure from the photon-baryon fluid would push back against the dark matter's collapse. This friction would dampen the sound waves traveling through the plasma, subtly altering their amplitude and changing the resulting pattern of anisotropies we see in the CMB. This is where the Planck satellite's precision becomes our most powerful microscope. By comparing the observed CMB power spectrum, the exact height and spacing of those acoustic peaks, against millions of theoretical simulations that include different strengths of dark matter baryon scattering, cosmologists can perform a cosmic exclusion test. They are effectively asking, how much friction can we add to the early universe before our predictions no longer match the pristine data? The answer is astonishing. The constraints are incredibly tight. The data allows for virtually no room for any non-gravitational torque between dark matter and ordinary matter in the early universe. The cross-section for such scattering, a measure of how likely these particles are to interact, must be vanishingly small, many orders of magnitude weaker than the strength of electromagnetic interactions. This null result is far from a disappointment. It is a monumental discovery in itself. It acts as a ruthless editor for theoretical physics, systematically ruling out a vast swath of potential dark matter models. Theories that proposed a significant communication between dark matter and baryons through a new, relatively strong force are now effectively dead. The CMB tells us that if dark matter does interact with us in any way other than gravity, it does so with a whisper so faint that our most sensitive detectors on Earth have yet to hear it. This doesn't just guide theorists, it directly informs the design of the next generation of terrestrial dark matter experiments. It tells them where not to look, saving countless hours and resources by focusing the hunt on the most viable parameter space, the realm of the ultra-weak or the purely gravitational. In this way, the silence of the CMB on this front is one of its loudest statements. It paints a picture of a universe where the visible and invisible realms are fundamentally separate, governed by different rules. The dark matter that shapes our cosmos does so from the shadows, a ghostly presence that guides the formation of galaxies with its gravity but remains aloof, its true nature still hidden behind a veil that the oldest light has only begun to lift. But the story of the CMB doesn't end with the simple statistics of hot and cold spots. Those patterns can be analyzed far more deeply, and when we do, we uncover a new layer of mystery that probes the very heart of how the universe was born. This is the quest for primordial non-Gaussianity, a search for subtle, hidden correlations within the cosmic microwave background that could reveal whether the infant cosmos was a place of simple quantum randomness or of far more complex and exotic physics. To understand what this means, picture the fluctuations in the CMB not as a static image, but as a vast three-dimensional field of hills and valleys, representing regions of slightly higher and lower density. Now ask a fundamental question about this landscape. Is it truly random? In the simplest and most elegant models of inflation, the answer is yes. The quantum fluctuations that were stretched to cosmic size are predicted to be Gaussian. This is a specific statistical term, but you can think of it as the ultimate in randomness. It means the distribution of these hills and valleys follows a very particular bell curve-like pattern. There are no hidden connections between them. A cold spot here tells you nothing about whether there will be a hot spot over there. The fluctuations are completely independent, like a static hiss on a radio between stations. This Gaussian signature is a direct prediction of the simplest single-field models of inflation, where one dominant energy field drove the entire hyper-expansion. The search for non-Gaussianity is the hunt for a deviation from this perfect randomness. It's the search for a faint but meaningful signal buried within the static, a whisper of structure within the chaos. Imagine listening to that radio static and suddenly hearing a faint, recurring pattern, a few notes of a melody that repeat just often enough to be sure it's not a coincidence. That melody would be non-Gaussianity. In the CMB, it would manifest as subtle, unexpected correlations between fluctuations of different sizes and in different places. For instance, it might mean that large-scale cold spots are slightly more likely to be surrounded by a specific arrangement of smaller hotspots, a kind of cosmic fingerprint that betrays a more complex origin. Why would finding such a pattern be so revolutionary? Because perfect Gaussianity is a hallmark of simplicity. Finding a deviation from it would be immediate, powerful evidence that the early universe was not simple. It would strongly suggest that inflation was driven by more than just a single, featureless energy field. Specific types of non-Gaussian signatures could be the smoking gun for multi-field inflation, a scenario where two or more fundamental fields interacted in a complex cosmic dance during those first moments. The interactions between these fields could have left behind precisely the kind of correlated patterns we would now detect as non-Gaussianity. Other, more exotic explanations could involve a non-standard beginning, like a bounce from a previous cosmological phase or effects from higher dimensional string theory, all of which could imprint their own unique, non-random signatures onto the fabric of space-time. The hunt for this signal is phenomenally difficult. The expected signal is incredibly weak, buried under the dominant Gaussian noise and obscured by later effects like gravitational lensing, which itself can introduce a secondary form of non-Gaussianity. It requires incredibly sophisticated statistical tools to tease out any potential signal. Scientists use measures like the bispectrum, which analyzes correlations between 3 points in the map, and the trispectrum for 4 points, searching for any statistical anomaly that can't be explained by simple chance. The latest data from the Planck satellite has placed the most stringent limits ever on these non-Gaussian parameters. So far, the universe appears to be astonishingly, almost boringly, Gaussian. The constraints are so tight that they have ruled out a huge number of more complex inflationary models, those that predicted a significant level of these hidden correlations. Yet, this null result is itself a profound discovery. It tells us that whatever process gave birth to our universe, it was remarkably clean and simple in a specific statistical sense. It powerfully supports the simplest class of inflationary models and places severe restrictions on how complex and interactive the physics of the very early universe could have been. However, the search is far from over. The next generation of CMB experiments will be so sensitive that they will be able to probe for levels of non-Gaussianity far below what we can detect today. They will be looking for that faintest of melodies in the cosmic static. If they find it, even at a tiny level, it would open a direct window into the dynamics of the inflationary era, revealing a universe born not from a single note, but from a complex and interacting chord of fundamental fields, forever changing our understanding of creation's first moment. And now we arrive at a mystery so subtle it was hidden in the very twist of light itself, a phenomenon that, if confirmed, would force us to rewrite the laws of physics. This is the enigma of cosmic birefringence, an effect that suggests the very fabric of reality might have a preferred handedness, a fundamental bias that violates one of the most sacred principles in physics, parity symmetry. To grasp why this is so revolutionary, we need to understand polarization and parity. The light from the cosmic microwave background is polarized. This means its electric field doesn't just vibrate randomly, it has a preferred orientation, like the light reflecting off the surface of a lake. This polarization is a fossilized record of the last time those photons scattered off electrons, and it carries invaluable information about the universe's conditions at that moment. Parity symmetry, or p-symmetry, is the principle that the laws of physics should be the same for a system and its mirror image. In a parity-symmetric universe, there is no inherent left or right, no cosmic preference for clockwise over counterclockwise rotation. The standard model of particle physics, our most successful theory of the fundamental forces, is built to respect this symmetry for electromagnetism. A photon's journey through empty space should not change its polarization angle. It should not develop a twist, yet that is precisely what a tantalizing analysis of the Planck satellite data seems to suggest. When scientists looked for correlations between two different types of polarization patterns, the standard E modes and the elusive B modes, they found a signal that shouldn't be there. This specific correlation is a direct signature of a rotation of the polarization plane of the CMB photons. It's as if every single one of those ancient photons had its polarization angle subtly twisted by about 0.2 degrees during its 14 billion-year journey across the cosmos. The universe, it seems, has been slowly turning the handle of a cosmic dial, imparting a faint but consistent rotation to the oldest light we can see. The immediate and most mundane explanation is, of course, systematic error. Perhaps our own galaxy magnetic field is causing this effect, or maybe there is some subtle miscalibration in the Planck instrument itself. But when researchers meticulously subtracted all known foregrounds and checked for instrumental artifacts, the signal stubbornly remained. It appears to be a genuine cosmological effect, a fingerprint left on the light by its long voyage through the vacuum of space. This is where physics gets incredibly exciting, because if the vacuum itself is causing this rotation, then our understanding of that vacuum is profoundly incomplete. This effect has a name: cosmic birefringence. In ordinary optics, birefringence occurs when light passes through a material that has a different index of refraction for different polarizations, like a calcite crystal, which splits a light beam into two. Cosmic birefringence implies that the vacuum of space itself acts like a giant, universe-sized crystal for CMB light. But what property of the vacuum could possibly cause this? The leading and most thrilling hypothesis involves one of the most sought-after particles in physics, the action. Actions are hypothetical, ultra-light particles that are a prime candidate for dark matter. More importantly for this mystery, they can couple to light in a very specific way. If a field made of such action-like particles permeates all of space, then as a CMB photon travels through it, its interaction with this field could cause its polarization angle to gradually rotate. This wouldn't be a violation of physics. It would be a new kind of physics, a new fundamental coupling between light and a mysterious field that we have never directly detected. The kicker is that this interaction would be parity violating by its very nature. It would mean the universe does have a preferred handedness on the largest scales, a fundamental chirality woven into the cosmos. The faint twist in the CMB's light could be the first indirect evidence for an entirely new cosmic field and a new particle, a discovery that would shatter the standard model and open a portal to a deeper theory of everything. The implications are staggering. It would provide a direct link between the invisible world of dark matter and the behavior of light itself. It would offer an elegant explanation for another great mystery: why the strong nuclear force appears to so perfectly respect CP symmetry, a puzzle known as the strong CP problem, for which the action was originally proposed to solve. The cosmic birefringence effect could be the thread that pulls these disparate puzzles together, weaving them into a single, beautiful tapestry of new physics. The search is now on to confirm this signal with next-generation observatories, to see if this faint rotation is truly the universe's way of winking at us, hinting at a hidden reality just beneath the surface of the empty void. After exploring the ghostly influence of neutrinos and the fundamental geometry of spacetime, we arrive at a question so fundamental it seems it should have a simple answer: how old is the universe? You might think that after a century of modern cosmology, this number would be settled, chiseled in stone. But the cosmic microwave background, our most precise timekeeper, finds itself in a quiet but persistent dialogue with other cosmic clocks, and their whispers don't always tell exactly the same story. This is the age of the universe discrepancy, a subtle tension that probes the consistency of our entire cosmological model. The age derived from the CMB is arguably the most sophisticated and precise measurement of the universe's birthday we have. It doesn't come from a single observation, but from a complex global fit. Scientists take the entire power spectrum, the detailed chart of those hot and cold spots, and run it through the supercomputer-powered machinery of the lambda cold dark matter model. They essentially ask, given what we know about dark energy, dark matter, and the laws of physics, what initial conditions and what expansion history are needed to produce this exact pattern we see on the sky? The answer that emerges with astonishing certainty is an age of 13.8 billion years. This isn't a rough estimate. The uncertainty is only about 20 million years in either direction, a mere rounding error on a cosmic scale. This number is so robust because it's woven from multiple interdependent threads within the CMB data itself, all pointing to the same conclusion. This value immediately passes a critical sanity check that plagued cosmologists for decades. In the 20th century, estimates for the age of the universe sometimes fell shockingly below the measured ages of the oldest stars, a clearly impossible situation. The CMB-derived age elegantly resolves this. 13.8 billion years is comfortably older than the ages we measure for the most ancient stars in our galaxy, which are around 13.5 billion years old. This allows plenty of time for the first stars to form after the Big Bang, making perfect logical sense. So far, so good. However, the plot thickens when we turn to other, more direct methods of cosmic chronometry, particularly the study of the oldest stars themselves. Here we enter the domain of stellar astrophysics, and the techniques are completely different. To age a star, astronomers don't look at the expansion of the universe. They look at the star's composition and its position on a chart called the Hertzsprung-Russell diagram. For the very oldest stars, which are found in globular clusters orbiting the Milky Way, the primary method relies on a fascinating fact. When these stars formed, the universe was almost entirely composed of hydrogen and helium. Heavier elements, which astronomers call metals, were forged later in the hearts of stars and scattered by supernova. Therefore, a star with extremely low metallicity must be very old. By modeling the evolution of these metal-poor stars, calculating how they burn their fuel and change over billions of years, we can estimate their ages. The best estimates for the oldest of these stars cluster around 13.5 billion years. On the surface, this seems to agree beautifully with the CMB. A 300 million year gap to form the first stars after recombination seems perfectly reasonable. But the tension isn't in the central value, it's in the error bars and the outliers. Some studies of particular ancient stars, using increasingly precise data, have sometimes suggested ages that push right up against, or even slightly exceed, the 13.8 billion year mark. This is, of course, statistically highly unlikely. If a star is measured to be 13.7 billion years old with a significant uncertainty, it could still be younger than the universe. But if independent methods start to consistently point toward ages that are 13.6 or 13.7 billion years, the comfortable 300 million year window for the first stars to form begins to feel very narrow, perhaps too narrow for our models of early structure formation. This is where another cosmic clock enters the conversation, one that is entirely independent of both the CMB and stellar evolution, the white dwarf cooling sequence. White dwarfs are the Earth-sized, incredibly dense cores left behind when Sun-like stars die. They have no internal energy source, so they simply radiate away their residual heat, cooling down over time like a dying ember in a cosmic fireplace. By measuring the temperature of the faintest, coolest white dwarfs in a cluster, astronomers can estimate how long they've been cooling. The oldest clusters give ages very much in line with the stellar evolution estimates, providing a strong cross-check that the stellar astrophysics is on solid ground. So, where does this leave us? We have two powerful, independent ways of measuring cosmic age. One, the CMB, looks at the universe as a whole and gives us a precise, model-dependent age of 13.8 billion years. The other, stellar astrophysics, looks at individual objects and gives us ages that are broadly consistent but occasionally hint at values that would make the universe feel a little too young for its oldest inhabitants. This isn't a 5-alarm fire in cosmology like the Hubble tension. It's more of a faint, persistent smoke alarm that prompts us to double-check the wiring. It forces us to ask, could there be a systematic error in how we model the very first stars? Are we misinterpreting the spectra of these ancient suns? Or more intriguingly, could it point to something deeper? If the universe were even 100 million years older than 13.8 billion years, it would actually ease the tension with the oldest star estimates. But the CMB data within the standard model leaves no room for that. This subtle push and pull reminds us that every measurement, no matter how precise, exists within a web of assumptions. The age of the universe isn't just a number, it's a benchmark for the consistency of our entire cosmic story, and even a whisper of discrepancy tells us there might be more to learn about the first chapters of time. After charting the grand geometry of the cosmos and weighing its most elusive particles, we now turn our attention to the finest brushstrokes on the universe's ancient canvas. This mystery lies in the subtle, high-frequency fade out of the cosmic microwave background's power spectrum, a region cosmologists call the silk damping tail. It's here, in the blurring of the universe's smallest details, that we might find signs of physics operating beyond our current understanding. To grasp the significance of this, let's return to the idea of the CMB as a frozen symphony of sound waves. The large-scale peaks we've discussed are the deep, resonant notes, the fundamental frequencies of the cosmic chord. But the music doesn't end there. It continues into much higher frequencies, representing smaller and smaller ripples in the primordial plasma. However, these higher notes don't ring out as clearly. They are dampened or muted by a physical process named after the physicist Joseph Silk. In the dense early universe, photons and baryons were tightly coupled, constantly scattering off one another. This created a powerful radiation pressure that resisted gravity's attempt to collapse matter into clumps. For the very smallest ripples, this photon pressure was incredibly effective. The photons would simply diffuse out of a dense region before it could fully collapse, dragging the baryons along with them and effectively smoothing out the fluctuation. It's like trying to form a dense snowball during a warm thaw. The structure simply melts away before it can hold its shape. This photon diffusion erases the smallest scale fluctuations, creating a smooth, exponential drop-off in the power spectrum, the damping tail. This isn't a flaw, it's a predicted and essential feature. The precise shape of this damping tail is exquisitely sensitive to the fundamental parameters of the universe. It depends on the density of baryons. The more matter there is to be dragged around, the more effective the damping becomes. It also depends critically on the number of light, relativistic particles that were present, like neutrinos and any other potential dark radiation. These relativistic species don't clump, they free stream, which enhances the smoothing process on small scales. The damping tail is therefore a powerful cosmic probe. By measuring its exact shape, how quickly and in what manner the small-scale power vanishes, we can take a precise census of the universe's contents and the physics at play during recombination. This is where the potential anomaly arises. When scientists compare the exquisitely detailed measurements of this damping tail from the Planck satellite to the predictions of our standard lambda cold dark matter model, they find a remarkably good fit, but not a perfect one. There are subtle hints of discrepancies, small wiggles and deviations in the data points that sit just on the edge of the error bars. The observed damping might be ever so slightly different from what our best models predict. It's as if we have a precise theoretical prediction for how an echo should fade in a concert hall, but when we listen carefully, the actual fade out has a slightly different quality to it. These tiny mismatches are the whispers of the damping tail anomaly. They are too faint to claim a discovery, but too persistent to ignore completely. So, what could they mean? One thrilling possibility is that they are evidence for additional relativistic particles, often called dark radiation, that were present in the early universe. Our standard model only accounts for the 3 known types of neutrinos, but many theories beyond the standard model of particle physics, including some string theory models, predict the existence of other light, weakly interacting particles, such as so-called sterile neutrinos. If such particles existed, they would have been relativistic during the CMB era and would have contributed to the Hubble expansion rate at that time. A faster expansion would change the timing of recombination slightly and alter how the photon baryon fluid behaves, which would in turn change the precise way the small-scale fluctuations get damped. The anomalies in the tail could be the ghostly signature of these unknown particles, a new form of matter that has otherwise evaded all detection. Another explanation could lie in a modification of the fundamental physics of recombination itself. Our models of how protons and electrons combine to form neutral atoms are based on beautifully precise quantum mechanics. But what if there was a slight error in our calculations of the atomic energy levels involved? Or what if an unknown process was injecting a small amount of energy into the plasma during this critical period, subtly altering the rate at which atoms formed? This would directly impact the photon diffusion process, as the timing of when photons stop scattering is everything. Even a tiny, early episode of reionization caused by the very first population of stars could, in principle, leave a faint imprint here, though this is considered less likely. The pursuit of these anomalies is a task of incredible precision, pushing our data analysis to the absolute limit. Future CMB experiments with even higher resolution and sensitivity are designed specifically to map the damping tail with unprecedented fidelity. They will measure these tiny fluctuations not just in temperature, but also in polarization, providing an independent and powerful cross-check. If the anomalies are confirmed, they would open a direct window into the particle physics of the early universe, potentially revealing constituents of reality that are completely invisible to our terrestrial particle colliders. The damping tail, once seen as merely the predictable fade out of the cosmic symphony, is now a frontier where the faintest notes might be telling us the most surprising story. And just as we measure the subtle fade of the damping tail, we find that the journey of the CMB's ancient light is not a straight and simple flight across the cosmos. Those photons have been on a roller coaster ride for billions of years, warped and twisted by the gravitational pull of everything in their path. This phenomenon, known as gravitational lensing, is a powerful tool in our kit, but it has now revealed its own curious inconsistency. This is the gravitational lensing tension, a subtle but critical mismatch that questions whether we fully understand the weight of the universe or the very nature of gravity itself. To grasp this, imagine the cosmic microwave background as the most distant, pristine screen imaginable, displaying a perfect pattern of hot and cold spots from the infancy of everything. Now picture all the matter in the universe, the galaxies, the clusters, the vast sheets of dark matter, sitting between that screen and us. As the CMB light travels toward our telescopes, it doesn't simply fly in a straight line through this cosmic landscape. The immense gravity of all that matter bends the fabric of spacetime itself, acting like a complex series of lenses that subtly distorts the light. It's as if that pristine screen is being viewed through a giant, lumpy, and ever-changing pane of glass. These lenses don't create new features, they instead stretch and squeeze the existing patterns, creating a faint, secondary layer of texture imprinted upon the primary CMB map. For cosmologists, this isn't a nuisance, it's a gift. By meticulously analyzing these subtle distortions, a process called reconstructing the lensing potential, we can literally map the total distribution of matter throughout the entire universe, including the invisible dark matter that makes up the bulk of the cosmic web. We can take the beautiful primary CMB map and use sophisticated statistical techniques to decode the specific warping it endured, effectively creating a three-dimensional mass map of everything that ever got in its way. This reconstructed map is incredibly powerful because it's derived from physics that is completely independent of other methods, like counting galaxies or measuring their motions. It's a direct, albeit complex, way in of the cosmos. The standard cosmological model, our trusted lambda cold dark matter recipe, makes a very specific prediction about how much lensing we should see. It tells us, based on the amounts of dark matter and dark energy we believe are out there, exactly how much those primordial photons should have been deflected. The tension emerges when we compare this prediction to what we actually measure from the Planck satellite's data. The observed lensing signal, the actual amount of distortion we decode from the CMB, appears to be consistently stronger than the model predicts. The reconstructed map suggests the universe's matter is clumped together just a bit more effectively than our best theory says it should be. It's as if we calculated the precise gravitational pull of every mountain range on Earth, but when we measured how much they actually bent passing light, we found the pull was noticeably stronger. This might sound like a minor accounting error, but in the world of precision cosmology, it's a red flag. It forces us to ask a fundamental question: is the problem with the scales or with the laws of gravity we use to calibrate them? One possibility is that there's simply more matter out there, or that it's clustered more densely than we've assumed. Perhaps our census of the universe's contents is still incomplete. The other, far more radical possibility is that our understanding of gravity itself is flawed. Einstein's theory of general relativity has passed every test with flying colors, from the orbit of Mercury to the bending of starlight around our sun. But it has never been rigorously tested on the truly colossal scales of the entire observable universe. Could gravity behave differently over these vast distances and epochs? Modified theories of gravity, often devised to explain dark energy without invoking a mysterious cosmological constant, can sometimes predict an enhanced gravitational lensing effect, potentially bringing the prediction in line with the stronger observed signal. Resolving this tension is a primary goal for the next generation of cosmological surveys. They will cross-check the CMB's lensing map with other, completely independent measures of the matter distribution, like the weak lensing of light from billions of distant galaxies. If all these different roads lead to the same overabundance of clumping, we'll be forced to seriously reconsider the ingredients in our cosmic recipe or the fundamental force that stirs them together. This subtle discrepancy in how light bends is more than a statistical hiccup. It's a potential stress fracture in the foundation of our model, a faint signal that the universe's gravity might have a deeper, more complex story to tell. Now we journey back to the very moment the universe first became transparent, to the precise physics of that pivotal transition from an opaque plasma to a neutral gas. This is the recombination history mystery, and it asks a deceptively simple question: how exactly did the lights turn on? We often picture this event as a clean, sudden flip of a cosmic switch, but the reality is far more complex and nuanced. The process of recombination, where free electrons and protons finally combine to form the first stable hydrogen atoms, was not an instantaneous event. It was a protracted and intricate dance of particle physics unfolding over tens of thousands of years, and the subtle details of how it played out are forever encoded in the cosmic microwave background. The mystery lies in the fact that our exquisitely detailed maps of the CMB are now so precise that they are beginning to reveal tiny discrepancies between the story we expect this ancient light to tell and the story it actually seems to be telling. To appreciate why this matters, we need to understand that the CMB is not just a passive snapshot. It's a dynamic record of the conditions during its own creation. The specific patterns of temperature and polarization we measure are a direct consequence of how quickly recombination occurred and the exact physical processes that governed it. Think of it like trying to determine the precise recipe for a cake by analyzing its final texture and flavor. A slightly different mixing time or baking temperature leaves a subtle but detectable signature. For the universe, the recipe is governed by fundamental constants and well-established atomic physics, things like the fine structure constant and the binding energy of the hydrogen atom. We think we know these numbers perfectly, and we plug them into our sophisticated computer models to simulate the recombination era. These models predict with incredible precision the exact fraction of free electrons at any given moment as the universe cools. However, when we compare these predictions to the actual CMB data from the Planck satellite, we find hints of a slight mismatch. The observed power spectrum, particularly on certain angular scales, suggests that recombination might have proceeded just a fraction of a percent differently than our most advanced physics codes calculate. It's as if the universe's oven was set to a slightly different temperature, or the ingredients were measured with a hair's breadth of difference. This tiny tension could be nothing more than a statistical fluke or an unaccounted for systematic error in the incredibly complex data analysis. But if it's real, the implications are profound. It could mean that our understanding of the atomic physics happening in the primordial universe is ever so slightly incomplete. Perhaps there were unknown, secondary processes at play, exotic energy injections or subtle particle interactions that slightly accelerated or delayed the capture of electrons by protons. The most thrilling possibility is that this discrepancy points to a variation in the fundamental constants of nature themselves. What if the fine structure constant, which governs the strength of electromagnetic interactions, was ever so slightly different 13.8 billion years ago? The precise timing of recombination is exquisitely sensitive to this number. A minute change would alter the specific energy levels of the hydrogen atom, changing the probability that an electron would be captured at a particular temperature. The CMB thus becomes the ultimate laboratory for testing the constancy of physics across cosmic time. A confirmed anomaly here wouldn't just adjust a parameter in a cosmology textbook. It would shake the foundations of physics, suggesting that the laws we hold as universal and immutable might actually evolve across the eons. This mystery forces us to listen even more carefully to the oldest light, searching for the faintest whispers of a cosmos where the rules themselves might still be written in pencil, not ink. And just when we thought we had mapped every subtle wrinkle and anomaly in the cosmic microwave background, a claim emerged so radical it seemed to pull the entire field of cosmology into the realm of science fiction. This is the mystery of the circular patterns controversy, a deeply polarizing debate over whether concentric rings imprinted on the oldest light could be evidence of events that occurred before the Big Bang itself, or even of collisions with other universes. The story begins not with a satellite's data, but with a specific type of analysis. A team of researchers, led by prominent physicist Roger Penrose, applied a technique called circularity statistics to the WMAP and Planck CMB maps. Instead of looking for the random, Gaussian fluctuations predicted by standard inflation, they were searching for something far more structured, patterns of concentric circles. The idea was that if our universe had been born from a cyclical process, or had collided with another, bubble universe in a vast multiverse, the energy released in such an event would have created ripples in the fabric of space-time. These ripples would then propagate outward as spherical gravitational waves, which would later imprint themselves as faint, circular patterns on the CMB like the ghostly echoes of a primordial splash frozen in time. To the astonishment of many, Penrose and his colleagues claimed they had found them. Not just one or two, but multiple sets of concentric rings where the temperature variance was noticeably lower than the surrounding areas. They called this evidence conformal cyclic cosmology, a theory suggesting that the Big Bang was not a unique beginning, but merely one in an endless series of eons, with the ghost of a previous universe leaving its mark on our own. The implications of such a discovery are, to put it mildly, earth-shattering. It would mean that our universe is not a self-contained island of space-time, but part of an infinite cycle of death and rebirth, or that it exists in a frothing sea of other universes with which we can, in principle, interact. It would provide a tangible, observational hook for the highly speculative concept of the multiverse, offering the first ever empirical evidence for a reality beyond our own cosmological horizon. For a brief, exhilarating moment, it seemed cosmology might be on the verge of its greatest revolution since the discovery of the CMB's existence. But extraordinary claims require extraordinary evidence, and the mainstream cosmological community responded with intense skepticism. The primary counter-argument is devastatingly simple. The human brain is a pattern recognition machine, and it is notoriously bad at distinguishing true signals from random noise. When you look at a complex, random map like the CMB, it is statistically inevitable that you will find some regions that appear to have concentric circles purely by chance. It's like seeing shapes in the clouds or faces in the static on a television screen, a phenomenon known as apophenia. Critics argued that the team's method of analysis was inadvertently cherry-picking these apparent patterns, and that when more rigorous, blind statistical tests were applied where the algorithm doesn't know what it's looking for, the significance of the circles vanished. The signal, they claimed, was just noise masquerading as structure. Furthermore, the standard inflationary model provides a powerful and simpler explanation for the entire CMB sky without needing any pre-Big Bang physics. The random quantum fluctuations stretched by inflation naturally produce a sky that is, on the whole, Gaussian and random. The presence of any coherent, large-scale structures like concentric rings would actually be a problem for inflation, not a prediction. The burden of proof, therefore, rests heavily on those claiming the circles are real. They must demonstrate that the patterns they see are so statistically unlikely to occur in a random Gaussian field that they simply cannot be dismissed as a fluke. To date, that burden has not been met to the satisfaction of the wider scientific community. The circular patterns controversy remains a fascinating and unresolved chapter in cosmology. It stands as a powerful example of how difficult it is to interpret the faint whispers from the edge of time, and how easily our desire to find meaning can shape what we think we see. It is a battle between a breathtakingly ambitious theory that promises to unlock the secrets of eternity and a conservative, data-driven approach that insists on ruthless statistical rigor. For now, the circles remain in the eye of the beholder, a tantalizing maybe, a ghost in the machine of the cosmos, reminding us that the oldest light might still hold secrets we are not yet equipped to understand. Yet for all the grand patterns and anomalies we've explored, some of the most powerful secrets of the cosmic microwave background are hidden not in the arrangement of its hot and cold spots, but in the very quality of its light, its color, and its spectral purity. This brings us to a profound and often overlooked mystery: the spectral distortion constraints, a set of rules written into the light itself that act as a supreme court, adjudicating which wild theories of cosmic history are permitted by the universe and which must be thrown out. To understand why this is so powerful, we need to think about the CMB not as a map but as a perfect thermal source. When you heat an object, it glows. A stove coil glows red, the sun glows white hot. the exact distribution of its light across different colors, its spectrum follows a very specific, predictable curve known as a blackbody spectrum. This curve is a fingerprint of pure thermal equilibrium, the signature of an object that has been perfectly and evenly heated. The astounding revelation from missions like the Cosmic Background Explorer satellite, or COBE, was that the cosmic microwave background is the most perfect blackbody ever measured in nature. Its spectrum is flawless to within a mere few parts per million. It is, for all intents and purposes, the ultimate thermal candle, burning with a purity that no human-made object can ever hope to achieve. This near-perfect blackbody nature is not just a curious fact, it is a monumental constraint on the entire history of the universe. It tells us that from the moment that light was released until the moment it reached our telescopes, the universe was an incredibly quiet and peaceful place. Any significant injection of energy at any point after the first year of cosmic history would have disturbed this perfect thermal equilibrium. It would have left a permanent scar, a distortion in the spectrum, like a single wrong note in a perfectly tuned chord. Scientists categorize these potential scars into two main types. There are what we call mu distortions, which would have been created by energy injections occurring between about 1 year and 100,000 years after the Big Bang. Then there are Y distortions, which would come from energy released after 100,000 years but before the epoch of reionization. Think of it like a pristine, ancient lake that has been perfectly still for millennia. If you were to drop even a single pebble into that lake at any point in its history, the ripples would eventually settle, but a sensitive enough instrument could still detect the subtle disturbance in the water's surface that the pebble caused. The CMB is that lake, and we have instruments sensitive enough to detect the tiniest of pebbles. The fact that we see no distortions means that no one threw a sufficiently large pebble. This simple observation rules out a staggering number of exotic and dramatic events that theorists have dreamed up over the decades. For instance, it powerfully constrains the existence of primordial black holes. If these hypothetical objects were abundant in the early universe, they would have voraciously accreted the surrounding gas, converting gravitational energy into radiation and flooding the young cosmos with X-rays. This energy dump would have heated the plasma, creating a clear and measurable Y-type distortion in the CMB spectrum. The fact that we don't see it tells us that primordial black holes could not have been numerous enough to constitute a major component of dark matter, effectively closing the book on a wide range of mass values for these objects. It also places severe limits on the decay of hypothetical exotic particles. If heavy, unknown particles from the early universe were slowly decaying over cosmic time, they would have injected energy as they died. The timing of their decay would determine the type of spectral distortion they would leave behind. The flawless blackbody spectrum tells us that no such widespread particle decay occurred, eliminating entire families of theoretical particles from contention. Even the annihilations of dark matter particles, if they occur with anything more than a minuscule cross-section, would have produced enough energy to leave an observable mu or Y distortion. The silence of the spectrum is deafening. It tells us that dark matter, whatever it is, must be almost entirely inert, interacting with itself and with ordinary matter through gravity alone. This makes the spectral distortions a uniquely powerful, if silent, probe. While other anomalies we've discussed show us where the universe might be weird, the lack of spectral distortions shows us where it decidedly is not. It forces our theories of cosmic history to be calm and orderly. It tells a story of a universe that cooled gently and quietly after its violent birth, without major cosmic catastrophes or energetic paroxysms. The next generation of experiments, like the proposed Pixie satellite, is designed to measure these spectral distortions with a sensitivity 1,000 times greater than COBE. They will be listening for the faintest of whispers, the most subtle of ripples. They may yet hear the echo of a tiny pebble, a hint of an exotic energy injection so faint that it has so far eluded us. Or they may confirm the profound silence, deepening the mystery of why our universe's adolescence was so remarkably and perfectly quiet. After navigating the profound silences and startling whispers of the cosmic microwave background, from the unsettling axis of evil to the ghostly tug of dark flow, our journey brings us to a pivotal turning point. We are no longer merely interpreting a static, ancient map. We are on the cusp of creating entirely new ones with a clarity and depth that promises to revolutionize our understanding of everything. The future of cosmology is being written now, in the designs of colossal new observatories that will stare deeper into the primordial light than ever before, armed with technology that borders on the miraculous. This final mystery isn't about the past, but about the thrilling and immediate future of discovery itself. Leading this new charge is an ambitious international project known as CMB-S4, the Cosmic Microwave Background Stage 4. Imagine this not as a single telescope, but as a coordinated network of enormous power. CMB-S4 plans to deploy an army of over 500,000 superconducting detectors across two premier observing sites: the high, dry Atacama Desert in Chile and the frigid, stable air of the South Pole. This scale is almost unimaginable compared to previous efforts. It represents a sensitivity improvement of more than an order of magnitude over any existing instrument. Its primary mission is to hunt for the holy grail of cosmology, the definitive detection of primordial gravitational waves through their signature in the CMB's B-mode polarization. But its ambitions stretch far beyond that single signal. With this incredible resolution, CMB-S4 will create an ultra-high-definition map of the CMB's temperature and polarization, allowing it to scrutinize every anomaly we've discussed. It will measure the gravitational lensing of the CMB with such precision that it will create a definitive map of all the matter in the universe, visible and dark. It will deliver a verdict on the Hubble tension, probe the nature of neutrinos, and search for the faintest imprints of primordial magnetic fields or any exotic physics that left even the tiniest mark on the early cosmos. Meanwhile, soaring above the distorting effects of Earth's atmosphere, the Japanese-led Lightbird mission will take to space, scheduled for launch later this decade. Its name stands for the light satellite for the study of B-mode polarization and inflation from dust. Lightbird's unique strength is its breathtakingly wide view of the sky. While ground-based telescopes can only observe a portion of the heavens, Lightbird will scan the entire cosmic microwave background from its vantage point in space. Its specialized goal is to hunt for the specific pattern of primordial gravitational waves on the very largest angular scales, the same scales where anomalies like the hemispherical asymmetry and the low quadrupole power are most prominent. By operating in the pristine environment of space, Lightbird will be exquisitely sensitive to these massive patterns, free from the interference of atmospheric noise. Its all-sky map will provide the crucial, independent dataset needed to confirm or refute the strange large-scale features that have puzzled astronomers for years, offering a clean, global perspective that is impossible to achieve from the ground. Already underway and serving as a crucial pathfinder for these colossal projects is the Simons Observatory. Perched high in the Chilean Andes, this facility is a collaborative effort between major universities and funded by the Simons Foundation. It represents the immediate next step, a dramatic leap in capability that is happening right now. The observatory is deploying a new generation of telescopes equipped with tens of thousands of detectors, designed to map the CMB polarization with unparalleled speed and sensitivity. While not as vast as the planned CMB-S4, the Simons Observatory is a powerful demonstrator of the technology and analysis techniques that will define the next decade. Its data will provide the first major upgrade since Planck, offering new insights into the Hubble tension and delivering improved constraints on neutrino masses and the optical depth of reionization. It is the vanguard, the first wave of a new era of precision cosmology that is already collecting data as we speak. The collective goal of these missions is nothing less than to conduct a full audit of the standard cosmological model. They will test its predictions with a precision that was unthinkable just a few years ago. They are not simply looking to confirm what we think we know. They are designed to find the cracks, the inconsistencies, the places where the model breaks down. The greatest hope for many scientists is that these observatories will find something utterly unexpected, a deviation so clear and significant that it forces a fundamental rewrite of our textbooks. They could finally detect the B-mode polarization from inflation, confirming our grandest theory of the universe's birth. Or they could find that the signal is mysteriously absent, pushing the energy scale of inflation so low that theorists would have to go back to the drawing board. They could resolve the Hubble tension by discovering a flaw in our measurements, or they could cement it, providing irrefutable evidence for new physics that operates across cosmic history. This is the profound moment we inhabit. We are no longer passive observers of the cosmos' story. We are active participants in its next chapter. The questions posed by the cosmic microwave background, questions about the universe's origin, its contents, its ultimate fate, and its deepest symmetries, are now being pursued with tools of breathtaking power. The next decade promises to be a period of unprecedented discovery, where the whispers from the edge of time will finally be heard in full voice, revealing secrets about reality that we are only beginning to have the courage to imagine. And so our journey through the 30 mysteries of the cosmic microwave background brings us to a profound realization. This ancient light, this echo of creation, is far more than a simple confirmation of the Big Bang. It is a dynamic, living dataset, the richest and most complex archaeological dig site in all of science. And with every new layer we uncover, we find not just answers, but a deeper, more beautiful set of questions. These anomalies, from the unsettling axis of evil to the ghostly tug of the dark flow, are not failures of our models. They are the very signposts pointing toward the next great revolution in physics. Each one of these 30 puzzles presents us with a critical binary choice. Is it a systematic error, a subtle flaw in our measurement or analysis that we have yet to fully root out? Or is it a crack in the foundation of our understanding, a genuine signal of new physics waiting to be decoded? The cold spot could be a vast, empty nothingness. Or it could be the bruise from a collision with another universe in the multiverse. The Hubble tension might be a calibration error, or it might be the first hard evidence that dark energy is evolving, or that gravity itself works differently on cosmic scales. This constant, thrilling tension between mundane explanation and monumental discovery is the engine that drives cosmology forward. It forces us to build better telescopes, to devise more sensitive detectors, and to think with more creativity and courage than ever before. What makes the CMB so eternally fascinating is that it is a conversation across 14 billion years. It is the universe's first and most important message to us, and we are still learning how to listen to all its nuances. The fact that this single snapshot of infancy continues to challenge our most brilliant minds is a testament to the sheer complexity and wonder of the cosmos we inhabit. These aren't just academic debates, they are quests to understand the fundamental nature of reality, time, and our own place in this grand scheme. The pursuit of these mysteries is what transforms cosmology from a collection of data, points into a truly human story of curiosity and exploration. So as we stand on the precipice of a new era with projects like CMBS-4 and the Simons Observatory, we are not closing the book on these enigmas. We are opening a new volume written with finer ink and sharper clarity. The next decade promises to be the most transformative in the history of cosmology, where we will finally have the power to distinguish between measurement error and cosmic truth. The greatest discovery may not be the confirmation of one specific theory, but the unveiling of something we haven't even dared to dream of yet. Stay curious, keep looking up, and wonder at the fact that the oldest light in the universe still has so much left to tell us. Now we want to hear from you. Which of these 30 mysteries captured your imagination the most? Was it the impossible fine-tuning of the flatness problem, the cosmic silence of the missing correlations, or the haunting possibility of cosmic birefringence? Let us know in the comments below. But as we push our understanding of these cosmic anomalies to the very edge, we inevitably brush up against the most speculative and mind-expanding idea of all, the possibility that our universe is not alone. This is the multiverse connection, a concept that transforms the cold, hard data of the CMB into a potential portal to realities beyond our own. While firmly in the realm of theoretical speculation, several of the most stubborn mysteries we've encountered have found in the multiverse a provocative and mathematically coherent, if unproven, explanation. Take the enigmatic cold spot, that colossal and inexplicably frigid region in the constellation Eridanus. While conventional explanations like a supervoid have struggled to fully account for its profound coldness, one radical theory proposes a far more dramatic origin. In the framework of eternal inflation, which suggests our universe is just one bubble in an endless, frothing meta-universe of inflating spacetime, it's possible for these bubble universes to occasionally collide. Imagine our expanding cosmic bubble gently bumping into a neighboring one. The energy released at the boundary of that collision would be immense. According to this idea, such an impact would leave a permanent, circular bruise on our cosmos, a specific signature of altered temperature and polarization that would appear to us as a vast, cold, and curiously structured anomaly. The cold spot in this breathtaking narrative is no mere void. It is a cosmic scar, the first tentative evidence that our universe has touched another. This line of thinking doesn't stop there. The perplexing hemispherical asymmetry, where one half of the sky shows significantly more dramatic temperature variations than the other, also finds a potential multiversal interpretation. Could this fundamental lopsidedness be a remnant of our bubble's own violent birth within the greater multiverse? If our universe formed unusually close to the edge of its inflationary bubble, the physics of that asymmetric environment could have imprinted a directional bias onto the very quantum fluctuations that seeded all structure. We would, in effect, be living in a cosmic neighborhood that's statistically unusual, forever carrying the mark of our specific address in the infinite multiverse. Even the strange alignments of the low multipoles and the axis of evil have been woven into this tapestry, with some theorists suggesting they could be traces of a pre-inflationary structure or the gravitational influence of a nearby universe. It is absolutely crucial to underscore the highly speculative nature of these ideas. The scientific community remains deeply divided on such interpretations. For many, these multiverse theories are not yet even falsifiable. They make predictions that are currently, and perhaps forever, beyond our observational reach. Critics argue forcefully that they are a textbook example of painting the dragon, of inventing an elaborate, invisible entity to explain a mysterious footprint, when the real culprit is likely a more mundane systematic error or a subtle flaw in our standard models that we simply haven't identified yet. They represent a monumental gamble. If future, more precise data washes these anomalies away, the multiverse explanation for them evaporates too. Yet the power of these ideas lies not in their proof but in their potential. They demonstrate how the most perplexing data points can force us to consider possibilities that shatter our conventional understanding of reality. The CMB, in this light, becomes more than just a picture of our beginning. It is a canvas upon which we might glimpse the contours of other worlds. Whether these hints are confirmed or ultimately discarded, they serve a vital purpose. They push cosmology to its absolute limits, challenging us to dream on a scale as grand